have your students from your college joined, or do they intend to join?
I don't know. I gave the phone number last time, and well, if they have got the link, they'll join.
But all the lectures of mathematical physics, they are very very helpful. I mean, I all the time keep on saying this, again and again. How I wish somebody did all this for us. So,
So
what
should
is
we
it?
start? What is it? I mean, it's five
Yeah,
five.
because otherwise your timing. So when they see that it has started, then they start just the next 5 7 minutes. Okay. So Dr.
Yeah, yes, ma'am.
Neetu, you should go or live on by after telling us that you're going live, and also
Yeah,
recording you should do that.
okay,
Okay.
yeah.
So welcome all of you to this evening of learning physics with conceptual and problem-based approach, organized by the National Academy of Sciences, India, NASI Delhi chapter, which is a 10-week course. Maybe it will be 11 or 12. It started on 27th of July 2020 between 5 to 8 p.m. and it is live on the YouTube channel of NASI Delhi chapter. And today we have amongst us Dr. Savinder Kaur, who is with us uh, on a second day today. May I have the slide of introduction of Dr. Savinder Kaur for mathematical physics, please?
I think you can
So,
skip that.
Dr. Savinder, it's a pleasure for me to introduce her to the audience and the attendees. Dr. Savinder Kaur is presently working as an associate professor at SGTB Khalsa College, University of Delhi. She has done her master's and a PhD from IIT Roorkee in the field of atomic and molecular collision physics. She has published her research work in several international journals, and she is an ardent physicist. She works on the R matrix formulation for molecular structure and collisions. She is a permanent member of Indian Society of Atomic and Molecular Physics, and as I said even on the last time, a very affectionate teacher, a teacher who is bothered about the problems of the students and the problems that the students face while understanding a particular concept, and she goes out of the way to solve them for the benefit of her students. Welcome, Dr. Savinder. I'm so glad that you accepted our invitation and agreed to give us a lecture. I really wished you had agreed for more and more lectures, but then definitely this is not the last time. So I'm sure we're going to enjoy many days together. So please welcome and please share your screen and
Yeah, yes, ma'am. I'm
share.
stop
Yeah.
sharing and ma'am will share now.
Yeah. Thank you for your kind words. And I
Really, ma'am.
definitely would like to thank the NASI New Delhi Organizing Committee, the chairman, Professor Ajay Ghatak, secretary, Professor Anurag Sharma, convener, Dr. Punita Verma, co-convener, Dr. Pushpa Bindal, the organizing committee, for giving me this opportunity. And I now start my uh, talk here by sharing my screen, and I hope it is visible.
It's coming. Yeah.
Yeah. Okay. So there might be a slight delay. So we have today's lectures, actually third and fourth lectures scheduled for integrals, and we would like to understand the complex integrals and how we are going to perform them, the arcs, the contours that are required, and the respective theorems. We'll go through all that. And in addition to that, we will, in the next part, consequently, we will try to understand the Taylor and the Lorenz series, and we will classify the singularities, which is the most important thing. And then we learn to evaluate the residue, and then we will learn how to, apply this residues to different integrals that we solve. So I just straight away start off now, and see, the idea is to calculate a complex integral. So if I have a complex valued function f, this function f is of a real variable. So I might pick up a pencil. The variable here is real, it is t, and it's in a fixed interval, say 8 to b. So I can define the function this form, where a ut and vt are going to be real valued, both of them. And this function is going to be integrable over an interval a to b if the functions u and v are themselves integrable. So the idea is that, everybody knows what is an integral over fx dx if I have an interval, let us say a to b. So in the real space, when you are having a real function, students are very much familiar with Riemann integration. And they also have a geometrical meaning associated to it, because they think that the area of the curve y, let us say the area of the curve y is equal to fx, right? And the x-axis is the geometrical meaning of this particular integral. However, when we are doing complex analysis and we are talking of complex integrals, we must say that other than some special cases, there are no corresponding helpful interpretations, geometric or physical, available for complex integrals. But to understand the complex integrals, what we have to understand is that where are we going to perform them? So we need to know the curve in the z plane on which we are going to perform this complex integral. So the idea is first to introduce to you the curves that we need. We have arcs and contours. So a continuous arc is a set of points x and y that satisfy this parametric equation. T again remains a parameter here. And if you see this curve in this graph, this A to B, the one you can see here, each point xy on the arc corresponds to a single value of t. So such an arc is called a Jordan arc. If you see this, or if you see this one, they are just smoothly going up. A simple arc, the curve does not intersect itself. Now it's important for us to take this into consideration. It does not intersect itself. And it happens that the starting point A, ending point B, so the value of ZA is not equal to the value of ZB when A is not equal to B. So as you can see from the second curve here, this is an example of a simple arc. The ZA is somewhere here and the ZB is somewhere here. These two don't match, and the endpoint and the starting point, they also don't match. So such an arc is a simple arc because we need to know the arcs on which we are going to perform the integrations. Then we have a simple closed arc, and it is defined for A not equal to B and ZA is equal to ZB. That means the starting point A and the ending point B, the function value at the starting and the ending point are the same. For this, you can look at this circle and look at the parametric form that we write for a complex number. We are used to writing a complex number z as r, e, iota, theta. So you take the theta as the t parameter, and the t parameter is now going from 0 to 2 pi. So z of 0 has the same value as z of 2 pi. We've learned this in the last lecture. So we know this. So the idea is that if I have a simple closed arc, the property required here is that the value at the starting and the ending point should be the same, but A and B are not the same. 0 is not the same thing as 2 pi, but the values of z's are same. So this becomes a closed curve. And the direction of the arc, this direction that I draw, the direction of the arc is the direction in which t is increasing. So if my t is increasing in this direction, that is the direction that I will consider as the positive sense of the arc. That is the idea, right? So as you see here, these curves are intersecting and crossing. So we are not concerned with these kind of curves. Otherwise, what we will do is we will consider this part as one closed curve and this part is another closed curve if we want to do any kind of integration. So we do not want intersecting curves to start off with. Then an arc or curve is smooth if their derivatives are continuous. So if I have this derivative continuous and if I have this derivative continuous without this iota, the psi prime, in the particular interval a to b, then I will have a smooth curve. And I can also write the length correspondingly as integral over dz and use this property that I can write dz by dt or z prime dt. And I'm writing here a starting point A and a starting point B. Please note there's a difference between these two integrals that are written here. This is an integral over the arc. You're moving on the arc and you are changing the dz. Here I am writing dz by dt into dt, and I'm writing the starting and the ending points. This anyway gives the length of the curve. The contour is a continuous chain of a finite number of smooth arcs. And we would always like to look for smooth arcs which are sectionally continuous. So if you have a piecewise smooth closed curve without points of self-intersection, we call it a closed contour. And it is the closed contour which we are interested in. If you see, this is a circle, this is a polygon path, this is another, let us call it a rectangle, and the direction, this is the positive sense, the direction we are giving. So in the direction in which your particular parameter is increasing, that is going to be the direction of the contour in question. Now, contour integrals of piecewise continuous or a smooth contour is defined in this manner. This is what I wrote there also earlier, but then I wrote only for the length. Now I've written the function here and I've also written the function here, but note the difference in which I'm writing it. The right-hand side of this is obtained just via formal substitution of dz as z prime dt. This equation depends on the function that you are using, and it depends on the contour. Look at the left-hand side here. And this is really a line integral in the xy plane. And it is definitely related to the vector calculus because you are used to understanding this thing now, that a complex variable is a two-dimensional vector. But the idea that I'm trying to put across here is that the line integral will always depend on the contour. But for certain functions, if you have a line integral which depends on the contour chosen, while for certain functions, if you have the line integral depending only on the starting and the ending point, then there might be a case that a line integral is the same as an integral over the starting and the ending point. That means there must be something about this function which we need to know. Okay, so this is the important thing in a complex integration. I'll repeat again. Left hand side is a line integral. Right hand side is an integral where you have a starting point and an ending point. So one integral depends on the starting and the ending points. One depends only on the choice of the contour that has been taken. So if the function is continuous and smooth and the limit exists independent of the choice of the subdivisions, then the line integral is equal to the definite integral. This is the property we will utilize most of the time when we calculate. And properties of line integrals are more or less the same as the line integrals that we have on the real space. So you can add them up separately. You can take out the constant. If you reverse the direction, minus sign can come up here, or this negative sign can come up here. It's just the same thing as saying reversing the direction of the contour. You can divide the contour into two parts and subdivide the integration. Again, you can change the starting, some connecting point in between, you can change. That possibility is there. But then there comes a very important property here, that you always have an upper bound of the function on the contour that you have chosen, and L is the length of the contour. Right. So the idea is always to use the positive sense. That means you are going in an anti-clockwise direction. And the region enclosed by the contour should always lie on the left. Now, this idea is the most important thing. It's just like this. This is your contour. You are actually moving on the contour like this, and everything that you have is on your left. So as you move here, everything is on the left. That's the direction of the arrow I'm trying to make. I don't know if it is clear, but I hope it is clear. That's the direction of the arrow. You're keeping everything on your left when you're moving on your contour. Okay, so let us understand now how we reach to to understand that this integral, let us say, depends on the path taken. So I'm giving you a function here, and I will request the students to try it and understand and correlate with the last lecture that we had. If you check this function by the Cauchy-Riemann equations that we had done in the last lecture, you will tell me whether this function is an analytic function or not. But irrespective of you telling me, I'm checking one thing and I'm asking you to do that. You're given a function here, and this function is piecewise continuous. You have to show that integral of this function over the path is path dependent. It depends on the path, right? Where C is the line segment from 0 to 1 comma 1. This is an ordered pair 1 comma 1. That means, what am I asking you? I'm asking you that I've given you a function, and I'm asking you to integrate this function from this point to effectively this point here, from 0, 0 to 1, 1. So what you do, you write a parametric equation for it. You write zt as 1 plus iota t. So x is t and y is t, and the parameter is changing from 0 to 1, right? So the integral over C1 fz dz, what I do is, this is your function. And look at what the change is done here. The y is expressed in terms of the parameter t, because you got this parametric equation. X is also written in terms of t, you got the parametric equation. Everything is coming from here, because if I write t plus iota t, when your t is 0, you are at 0. When your t is 1, you are at 1 plus iota, and that's the point we are talking about. That's the line segment in question. Okay, so obviously we know this is the z expression, so we can calculate the dz, evaluate this thing, and we get this expression. Now, the idea that we want to make. We want to say that integral over C fz dz is path dependent. Now, one student made a choice. Let us say that person took a choice from moving from O to P along C1. But somebody else chose to move from, let us say, O to X and then to Y, right? So O to X and then X to Y. Somebody would like to take this path. So the contour in question now is A1 and A2. So along A1, what is the parametric equation that I can write? And along A2, what is the parametric equation that I can write? So let us consider the path. We have path C2. Now path C2 involves two arcs. From 0, 0, you go to 1, 0. So if you go from 0, 0 to 1, 0, what you have to take care, what is the variable which is changing? 0 to 1, only x is changing. So I can just simply write t, and the variable is changing from 0 to 1. So x is effectively t, and there is no change in y, and y is constant and it is 0. So y is 0, and dz is dt. So along A1, I know this is the property. Similarly, along A2, I try to see, I am moving from the point 1, 0 to 1, 1. So here your x is constant is 1. This is your x, it is constant is 1. And it is the y which is moving from 0 to 1. So I can put it as a parameter t going from 0 to 1. And I write the expression for z as 1 plus iota t. So please note this one, this is important, because the starting point is from t equal to 0. So 1 comma 0 is your starting point for A2 arc, right? So you write your integral A1 fz dz, you change your parameters according to the y and the x for A1. Just do that and you calculate and you get a value as minus half. The same thing you do for A2. When you do for A2, okay, so maybe that I think you can do it. So for A2, you will substitute here the values and you effectively get this, right? So when you sum over the values of A1 and A2, if you just carefully see, A1 is minus half. So if I add minus half to this, I'm going to end up with this value. Now this value, which is in the green box, a path which I have taken like this. I have taken a path as A1 and I've taken a path as A2. Okay. So when I have a path as A1 and I have a path as A2, I am getting this result. But when I had taken a path as this C1, I got this result. Now this is different from this. So it is just giving me an idea that I have used a function and there must be something in this function because the value of the integral is depending on the path that I have taken. So this is a very important conclusion. Because now, next what I will do is, anybody has an answer to the question I asked just now, is this function analytic? This is from the last lecture that we did. How do you check for analyticity of a function? Does anybody know it? Okay, so anything from the chat? It is not analytic. So basically, it is not analytic or it is not differentiable. You checked this thing from your Cauchy-Riemann equations. Del u by del x is del v by del y. And you also checked it by del u by del y is minus del v by del x. So you actually get only 1 point. So the idea is that the function is not analytic. Okay. So if your function is not analytic, then it is depending on the path. So this is a very important concept you learn. Now you go ahead and see that if your integrand is analytic, then what happens? Then again, let's try. You take a function as z squared. You know this z squared function is an analytic function. You know it. Okay, so let's try it. Now we consider here, let us say, two paths. A path from 0, 0 to 2, comma 1, and a path from 0, 0 to 2, comma 1 again. Only thing is, one you're traversing from here to here via this C1 path, and the other one you traverse from 0, 0 to 2, 0, that is A1 path, and from 2, 0 to 1 by A2 path. The equation of this line, if I see for C1, the equation of this line is very clearly x is to y. So instead of writing a t parameter, I can also use a y parameter. So I can just replace x as 2y. So z is 2y plus iota y. Okay, so this is what I have. So I just simply use that value for the function. I need a z square. I differentiate it. I put the differential here and I solve it and I get a value. So the idea is to check whether if I go from A1 and if I go from A2, the values, the sum total of these two integrals, do they come out to be the same as the value that I got across C1? Okay, so the path C2 involves these two arcs. So I have to do this. Now along A1 again, your parameter is x. X is the parameter which is changing. Y is not changing. So I can write the parametric equation as x plus iota 0. Calculate the dx, and hence again along arc A2 here your x is constant. It's the y parameter which is changing. So x is constant, which is 2, and the y parameter which is changing. So I write iota y. So z is iota y. I mean basically this is dz is iota y. That is what is important because z is still 2 plus iota y. That's a typing mistake. And you put the function value here, right? So you have this value put up here. Now note this point, along A1, you will use the functional value according to the parameter choice that you made, z square. Z was x plus iota 0 along A1, and z is 2 plus iota y along A2. So you calculate these values, solve for whatever values you have. Everybody can do that. You end up with this result. Now this result happens to be the same as this result. So what happened? You went from this path, which was your C1 path. You also took a A1 path and an A2 path. So you took an A1 path and you took an A2 path. You solved your integral along this, you solved your integral along this, right? So this integral and this integral, the value that you got was exactly the same as this integral C1. However, what do you note? What have I written here? I have written here the direction of A1 like this, the direction of A2 like this, but I have written a reverse direction for C1. please note this. I've written a reverse direction for C1. Why? Because I know integral over A1 and integral over A2 summed up is actually equal to the integral over C1. So if I just bring it on the other side, I make a minus, I actually reverse the sign. This is a property which we have learned. So if I reverse the sign, what have I actually done? I have closed the contour like this with the directions here for A1, for A2, and for C reversed. So the curve is now closed. So effectively, what do you see? That if your curve is closed and the function inside is analytic, your integration over that function is giving you a result which is 0. And very soon we will read about it. It is nothing but a theorem that you're going to study. So can you evaluate this question? Evaluate the contour integral z bar dz along the line 0 to 1 plus iota, and just give me an answer quickly. Okay, somebody has written this function is not analytic. I think we have already solved this thing. Why is this function not analytic? If somebody can try and tell me that. The function is a z square. And when you write a z, you write it as an x plus iota y. You write it as a whole square. So this is effectively x squared minus y square, okay, plus iota. You have a 2xy. This turns out to be your u, because we are writing this as omega, which is your range space. So your transformation equation, this is your uxy, and this happens to be your let's call this x comma y, right? So if you find out a partial derivative of u with respect to x, what do you get? Partial derivative of u with respect to x, what do you get? You get a 2x. And a partial derivative of v with respect to y, what do you get? You get a 2x. They match. This is the first Cauchy-Riemann equation. This is what I told you to check. When you find out the partial derivative of u with respect to y, you get a minus 2y, right? And then when you find out a partial derivative of v with respect to x with a minus sign, what do you get? You get a minus 2y. So it matches everywhere in space where x is equal to y, everywhere. Oh, why should you get confused? Z is 2y plus iota y is 2y is any x. This should not be a confusion. X is any parameter. It's a line, and this is exactly what you are getting. You are getting for any x equal to y, you are getting this as a differential. Okay, so it should not matter. This is just x. If I had just written it as x, okay, as x plus iota y, and if I had chosen x as, let us say, 2t, and I had chosen y as t, and the parameter t would actually go from 0 to 1, it's the same thing. So it should not change. It should not matter you. It should not affect. Okay, it's okay. Who is this? Abhiram Singh. Okay, so that's good if it's okay. So it's quite clear. So the idea that I'm trying to make is, when you had a function and the function was not an analytic function, then it was path dependent, your integration, contour integration. And the moment your function is analytic, it becomes independent of the path. And another thing is that if it is a closed curve, calculating a curve, you get into for this. Okay, so I didn't see that coming up. So let me just check it up. You have to evaluate the contour integral for z bar dz, and you know that this z bar is not an analytic function, but still you would like to calculate it from 0 to 1, 1. So the idea here is that, how to use something directly from the function which is given to you using the functional form itself. So simply write the z bar here. I know what is z. Z is x plus iota y. So I can correspondingly write dz as dx plus iota dy. I can use the path given to me 0, 0. Okay, so the path is to go from 0, 0 to 1, comma 1. That's the path you've been asked to move on. So the parameter t, if you see along this, is just going to change from 0 to 1. So that's exactly what's happening. We are taking a parameter changing from 0 to 1. So you put the values of the parameters and you should get a result as 1. Now this is an interesting thing that we have learned about a function being analytic and not being analytic. If it is analytic, it does not depend on the path, and therefore the closed contour integration is going to give you a 0. So this is one thing we have learned. Now let's go ahead and learn another concept. Now what is the concept? You're supposed to evaluate the contour integral around a closed contour. Now you've closed your contour. The contour is closed and you're taking it as a unit circle. So let's take this as a unit circle, and let's assume that this is a circle because it doesn't look like, but let's assume it as one. Okay. And because it is a unit circle, so I would like to say this is mod of z equal to 1. And this is the x-axis and this is your y-axis. Right. I want to calculate an integral dz upon z. So your z is r e iota theta, your r is 1. So effectively z is e iota theta. You find the differential, it is going to be iota e iota theta d theta. And if I integrate, starting point is 0. I take a full circle and I come back, my ending point is 2 pi. So that is why this is a closed contour. And it is in fact a simple closed contour. So when I evaluate here, I'll get an answer as 2 pi iota. Your next example here is to integrate over this closed loop, but still you have to integrate for what? 1 upon z to the power of n. And when you do the same integration, you have put the same variables in, your z is still e iota theta, right? So e iota theta, and this is n coming from your de Moivre's theorem. Iota e iota theta is the dz and the d theta. When you integrate it, you get something like this. Now this tells you that you can't say anything for n equal to 1, but when your n is not equal to 1, this turns out to be a 0. So what do you learn? You learn something very interesting from here. It's just mathematics, but there's a physical thing associated. The moment you had an integral over the curve as 1 by z dz, this is a d, you got a 2 pi iota. And the moment you increased it as 1 z to the power of n dz, you got a 0 if your n is not equal to 1. Because for n equal to 1, effectively, you already got it as a 2 pi iota. You already got it. And you are working on a closed contour. So that's why you have this circle in it inside the integral. So what do we learn from this? Anybody wants to give anything? Okay, so nobody's writing, so maybe I'll wait for an answer. So, or maybe you'll get the answer in my next slide. So the idea that I'm trying to make is that this is going to give you some indication of simply and multiply connected domains. Now, if I had a circle, ellipse, a square, or anything that I had here, I mean, all the diagrams that I had drawn earlier, ellipse, circle, square, they will be simply connected. Somebody's saying for odd number, it should be an odd multiple. Let's come to it. Let's try to understand what you're saying. Maybe you didn't get the question that I put up. I'll put it up again. But before that, I'm trying to come to the simply and multiply connected domains. And I'm giving you an idea here that what is a simply connected region, what is the multiply connected region. So that is what you have to understand first. Look at this one, the one which is on the left hand side. This is completely shaded, and we have a contour here, C. If I shrink this contour, it will not leave the domain. It's going to stay there. It might shrink off to a point somewhere here or here or here, anywhere. It doesn't leave the domain. However, if I have these holes into this, where, I mean, they are basically singularities. So when I shrink it, it's going to leave this place and come into this portion. Or maybe if I had a contour somewhere here, and if I would shrink it, it would come here. So it leaves the multiply connected region. Or if I have a ring like this, if I shrink it, it's going to come and shrink to some point inside here. So the idea is that if you have something like this, it is a simply connected region. And you have something like an annular domain, you have a multiply connected region. Now, why are these regions important and what have they got about themselves? That we want to understand. So a simply connected region will not have any holes, while a multiply connected region is one which does have holes. And by holes, we tend to say singularities, because we will try to, isolate our singularities. We will try to draw a contour about a singularity so that we are able to calculate its contribution towards the integral. That's the idea of this whole lecture, to do that. However, what we want to understand here is that in the simply connected region, we can apply the Cauchy-Gorsuch theorem, which you have right now actually already evaluated. Now, what did you evaluate, if you remember? You had a C1, C path, okay, and you had an example like this, where you had taken a path as A1 and you had taken a path as A2. And what you had got is that the contribution along A1 and A2 were exactly the same as the contribution along C. So what you had done is integral over A1 and an integral over A2 minus an integral over C1 or a C had given you a 0. So actually you had closed the curve and reversed this direction of this particular arrow. So Cauchy-Gorsuch theorem says the same thing. It just says that if your function is analytic, if your region is simply connected, then the integral of that function in that simple closed contour, on that contour that you have taken in that particular domain, which is simply connected, this integral is going to go to 0. This means if I have, let us say, this curve that you can see, if I have two contours, let us say I have C1 and if I have C2, and they both are lying in a simply connected domain and have the same initial and terminal points Z1 and Z2, then the integral over C1 and the integral over minus C2 together are going to form a closed contour, right? And this is going to hold for any closed contour, that the integral over C1 plus the integral over the opposite direction, because I have to close it, So I'll just reverse the direction here. This is going to be 0 because I have to close it. So it's also the same thing. It means you start from here, you end from here. Take any path you like on a simply connected region. Your integration over that path is going to be the same thing. So it gives me what indication? It gives me that this is the same thing as an integral from, if this was an A point and this was a B point, it's exactly the same thing as starting from A and B and just evaluating the integral at the endpoints. Okay, so this becomes a really important thing. When your function is analytic, the line integrals from Z1 to Z2 are independent of the path chosen. But remember one thing, Cauchy-Gorsuch speaks only as long as it is a simply connected domain, right? And the integrand is analytic in that particular domain. That is when we are saying all this. So there's an interesting thing to learn here from the Cauchy-Gorsuch theorem. And this is what you have evaluated and this is what you learn here. Let me start, let us say, from this point, and let me call this point as A. Let me move from A to C1. Remember, we have to keep it as a simply connected region, and the idea was to keep everything on your left. So I am moving along this direction. Now I go along this particular C1. I still keep everything on my left and I go along C1, right? I move along C1 here and then I come back here in the reverse direction and then I move along C2. Now everything is simply connected. The very small difference between, starting point A to this point and just taking a curve in this direction. Now this is what is the thing that we are doing. We are making the whole region simply connected. So what do I have? I have an integral over C and an integral over C1 is going to give me a 0 from Cauchy-Gorsuch theorem. So from this figure, what did you note? You just simply note that the directions of both the contours were opposite. And the moment they were opposite, you just summed them up and you said that they were 0. You also have said, okay, if you reverse the directions, what to do? If you reverse the direction, just introduce a minus sign here. Take it on the other side. So if you have a contour integration over C, it is the same as a contour integration over C1. This is a very important application that you learn. Okay, so what have you learned? If your directions are opposite, you are summing over both the contour integrals and you're getting a 0. If the directions are same, you are getting the integral over C and C1 as same. But don't think that they are different. They're exactly the same things. You wrote the same thing, you only changed the direction of the contour. That's all. You just reversed it. Okay. So sometimes why this is important is that sometimes we would like to integrate over C and not on C1, or maybe we would like to integrate over C1 and not on C. So this property you can use. Again, if you have a function which is analytic and you have a non-overlapping simple closed curves, let us say not one simple closed curve, but multiple of them making a multiply connected region, but something like this, then what to do? So you go back to the same understanding. In the Cauchy-Gorsuch, you had an integral over C. It was same as an integral over C1. So if I had regions like this, I could say an integral over C is the same as an integral over C1, the same as C2 plus this and so on. I can just sum over all of them and write this. This is a very important implication that we get. And mind you, this whole system, if you see, is a multiply connected region. But Cauchy-Gorsuch theorem is being applied only for a simply connected region. So that means you are going to, keep on cutting places here, keep on joining them, keep on going in the other direction, go along this direction, then go here, then go up here, go along this, because the idea is to keep everything on your left and henceforth keep moving. And hence you reach this particular relation. Multiple poles concept is going to come sooner. You use everything when you solve dipoles, quadrupoles, and so on. So that is where we are going to use them. Okay, so that was a question in the chat. So, right, so the Cauchy-Gorsuch theorem for multiply connected is explained here, but I don't think I'll go through it because I have already explained all this mathematics here. The main idea that I want to put across here is that you prove that theorem using deformation of contours. So using the principle of deformation of contours, you just simply use this fact that if you have the contours in the same direction, you can evaluate the contour integral over C1 or over C2. They are going to be same. So that's the idea we make. But we keep one thing in mind, that the Cauchy-Gorsuch theorem is only for simply connected regions. And we have been saying and again and again that the function is analytic. But now we would like to understand the Cauchy's theorem. Now, Cauchy's theorem has an additional factor attached to it. It says that the function is analytic, just like Cauchy-Gorsuch, but it also has a derivative. That means the functional derivative is defined and is continuous at each point in the region. Now that region may be simply connected or it may be multiply connected. So you have both the options available here. Now you don't have to stick to the simply connected region every time. So Cauchy theorem is a more general theorem. It is telling you that if your function is analytic, if its derivative is continuous, and if your region is simply connected or multiply connected, for every closed path, the integral over that particular function is going to be 0. Only thing is this function should be analytic, should have a derivative which is continuous. So just simply, if you just see these contours immediately, if you know this property, you can solve each and every integral in one go. If I have an integral c dz, what do I have here? I have a 1. This one is what? A constant. So the function is 1. In this, I have a function as z. In this, I have a function as z minus z naught. In this, I have a function z to the power m. So these integrals are involving all these functions, and all these functions are analytic functions. They have continuous derivatives, and henceforth, an integral over a closed path is always going to give me a zero via Cauchy's theorem. This is what we use. Okay, so let's go ahead and let us see the consequences of Cauchy's integral theorem that we have. Now, as I mean, this I have actually pointed out earlier also. You have a starting point, let us say A, and you have a starting ending point B. So if you have a function fz and it is analytic in a simply connected region R, then the integral from A to B fz dz, this particular integral is independent of the path if you are in a simply connected region. So how do we prove that? We just simply prove it by taking a closed curve. So if you see, this is written as AEBDA. So this is a closed curve. And you are breaking it up into two parts, AEB and BDA. That's what you do. But just remember, BDA is this direction, the reverse direction of the arrow that you see. So I take it on the other side, this is a minus direction, and this happens to be AD and B, AD and B. So integral over C1 is the same thing as integral over C2. It just simply tells me that it's going to be independent of the path. So this is an important thing that you have learned. So you have done earlier also. Now I come to this question which I had asked you, and I'm doing it again, but in a different sense, because we are now going to understand from the Cauchy's theorem all these things. You have to evaluate an integral dz upon z minus a. Now C is any simple closed contour. So I have a C as any simple closed contour. And this point z is equal to a is outside the contour or it is inside the contour. So let us say this is your A point outside the contour. And this happens to be the contour. This shaded region that you see is the contour in question. It's a simple closed contour. So it has no singularities in it. So when your point lies outside, the integral over C over this closed curve via Cauchy's theorem should give me a zero. I think that should be clear. Yes, the answer is zero. Somebody's given it. Good enough. Now I put the singularity inside. When I put the singularity inside, I always draw an epsilon neighborhood about it. I try to write a parametric equation for this circle. And I try to use the concept which I have just now learned, that a contour integration over C is the same thing as a contour integration over C1. And that is what I'm going to apply. So the point Z is equal to A, it lies inside. The contour over C, I will use as an equality with the contour over C1. I use the parametric equation Z minus A is epsilon E iota theta. And I calculate it, I get a 2 pi iota. And very recently you got a 2 pi iota, right? And you had to answer to me the understanding. I'm still waiting for that answer. Okay. So we go ahead here, we evaluate an integral dz, z minus a to the power n in this case, again use the same property that contour integral over C can be replaced by a contour integral over C1. You still use the parametric equation like this, substitute your values, and you still get a zero. What does it imply? Anybody? I don't see any chat. So Bhavna would like to answer. So higher order pole, so what does it mean? What does a higher order pole mean here? What would you like to imply from the higher order pole? Okay, so maybe it's still you've got to figure it out still. Okay, so can you find an answer to this integral? This you should be able to solve in a jiffy. Please note the contour consists of a circle z equal to 3 described in a positive sense together with another circle mod of z equal to 2 but described in the negative direction. So the integral of this and I'm showing you the figure here. So what is the answer to this? Okay, so maybe I can just continue because I don't see any answer. I mean, I don't know why I'm not seeing anything. So, okay, z square plus 16. So if I see the denominator here, z equal to 0, I have a singularity, and z equal to plus minus 4, I have a singularity. So I have a singularity here, and I have a singularity here. Both the singularities sit outside the annular domain. This is z equal to 0. The singularity again sits outside because you have to be, careful about the contour that has been given to you. Z equal to 3 described in the positive sense, that's a positive sense. Z equal to 2 described in the negative sense, that's a negative sense. So you've basically been asked to use this particular annular domain. Okay, so in this annular domain, if you're calculating, you don't have a contribution of these singularities coming up anyway, because Cauchy's integral theorem just says that if your function is analytic in the region and is differentiable and the derivative is continuous, then the integral over that contour should give you a 0. So this is what you have. The points, they lie outside the shaded region, and therefore by Cauchy's theorem, your result follows that it should be equal to a 0. Okay, now we come to the Cauchy's integral formula, the basic application that we have here. Now, there's something really interesting about Cauchy's integral formula that we learn, that the value of an analytic function at an interior point in a simply connected region, you can determine. How? By integrating the function around the curve surrounding the region. Now, this is an important thing that we learn. That means you are able to determine the value of what? Of the analytic function at any point inside the simply connected region. And you just do it by just simply integrating the function. It also implies that any change in the value of the function at the boundary is going to bring about a corresponding change in the value of the function at the interior point. So if your function is analytic in and on your simple closed contour, and if your A is any point, you can define the functional value at that point by giving this expression. So remember one thing, when we say fz here, this fz has to be analytic. We are not talking of z minus a, we're just talking of the fz being analytic in and on the simple closed contour. And we also have the nth derivative of the function defined at z equal to a. And when you have the nth derivative here, it is defined by this formula. There's an n factorial coming up and there's n plus 1 coming up in the denominator's power. The idea here is n starts from 1, 2, 3, and so on. The moment your n is 0, you have reached this special formula. So two important results from Cauchy's integral formula that you learn. If you know the function, right? If the function fz is known on the simple closed curve C, then the values of the function and all its derivatives can be found at all the points inside C. Now, why are we saying this? Try to understand. It's a simple closed contour. Choose any point. Any point can be your A point. So at every point, you can calculate the value of the function. You can also calculate the value of the derivative. What is this? Fna is the nth derivative of the function evaluated at a point A. So your A point can be anywhere. So at all points, you will get the information. This is the beauty of complex variable. So if a function of a complex variable has a first derivative, all its higher derivatives exist in R. So this means that in this respect, complex analytic functions are going to behave in a more simple way than your real functions, because if you have one information, then the information about all other higher derivatives you get to know. Okay. Okay, so here's a question for the students. If you can try this, maybe I can wait for a second or two. It's very simple. Find G2, use your Cauchy's integral formula. Evaluate G2 if this is the function that is given to you. Your contour is this, and it is described in the positive sense. Okay, one person is given me an answer as 6. Let us see if 6 is an answer. Anyone else would like to give any answer? Okay, so maybe I will go ahead and let us see. This is the contour that has been given to you. Mod of z is equal to pi. Okay, and z minus a 2z square minus 6, and you have been asked to calculate at 2. That means this a is supposed to be your 2. So this is 2 comma 0, right? So if you just, maybe I just reduce the size so that you can see the question along with what I'm trying to say. If you see this expression, and if you see this expression from the Cauchy's integral formula, the only thing I have to do is I have to multiply 2 pi iota with f of a, replace this f by the g, it's the same story. Your gz is 3z square minus 6. So your f of z is your gz at z equal to a, okay? So gz is 2 pi iota times this, and you evaluate this at z equal to 2, and when you do this evaluation at z equal to 2, you get an answer as 12 pi iota. So you don't get a 6, but you get this as a result. Okay, so you got this, and let us see this one. So find an integral over a function gz. Your gz is 1 upon z square plus 4. Let's first solve this one. We'll solve this later. So the function is 1 upon z square plus 4, and you have been given this contour. So when you have been given this contour, and we know z minus iota means your center point is going to be 0, comma 1. So this is your center here, and the radius is supposed to be 2, and this is the contour in question. So this C in the positive direction is the contour in question, anti-clockwise direction. So the function given to you is 1 upon z square plus 4, and you have been asked to integrate over this particular contour. Okay. So what you can do is you can write the given function in terms of partial fractions. This is the easiest way of doing it. When you write it in terms of partial fractions, see how the denominator is going to go to 0. When your z is minus 2 iota, your this particular fraction blows up. And when your z is 2 iota, this particular fraction blows up. So what is the idea? The idea is for this part, z is equal to minus 2 iota. That means a point somewhere outside here has a singularity contribution. And for z equal to 2 iota, that means this point has a contribution. Now this point lies outside the minus 2 iota. So it's not going to contribute to the integral. The only contribution we will have is going to be from here. No, the answer is not going to be 0 because we have 2 parts, right? So when you have the point in the interior, you will apply the Cauchy's integral theorem. And when you apply the Cauchy's integral, you have fz dz, z minus 2 iota, 2 pi iota times the functional value. This function here at the particular point. But what was your function? Your function was just 1, just 1. So this is the one function. and your result is 2 pi iota. However, for this case, where it lies outside, it is an exterior point, in that case, you're going to get a 0. Okay, so in that case, you get a 0, and this 0 you get from here, and here you get a 2 pi iota. 1 by 4 iota you are done because you made a partial fraction, so you get your result as pi by 2. So the idea is that you just simply used the Cauchy's integral formula like this. Directly you are learning to apply the Cauchy's integral formula to this or to this. So function here, f of z, you must relate the fractions. Your function is -1 fz, here your function is 1. Here your z minus a is z plus 2 iota. So your a is minus 2 iota, and here your a is 2 iota. That is the idea. So you have to be very careful whether your point lies inside the contour or it does not lie inside the contour. Now repeat this whole thing and repeat this whole thing and check it up for gz 1 upon z square plus 4 whole square. Just check this out. Now check it for this. Now if you check for this, what do you get? Your function gz is 1 upon z square plus 4 whole square. I just factorize and I write the denominator. Now there's another important thing you learn. Look at the contour. Maybe I will just kind of draw the contour for you. If you can give me a moment, I can just take a snapshot of this contour. That's going to save our time. And put it here for you. Right, and let's make it a little shorter. Okay, so this is the contour in question. And this is your function given to you. Now look at the function. What part of the function is analytic? The moment your z is 2 iota, it lies inside here. This one creates a singularity, and that singularity is here. But this one does not. So this function is analytic in this simply connected region. So what I can do is I can treat this form of fz as this. Just simply I can do that very clearly. And what I have to check now, 1 upon z minus a whole to the power of 2, and I have to connect to this Cauchy's integral formula. If this is 2, this n plus 1 is 2, so the n is 1. So how do I calculate? I integrate fz dz and z minus 2 iota whole square, and I just simply write 2 pi iota upon 1 factorial because n is 1. I find out the first derivative because n is 1, and find out the derivative of what? Of this function. Which function? This function, which was analytic in that particular domain. So I'm applying the Cauchy's integral formula. I'm keeping in mind that this fz has to be an analytic function. So in that analytic function, I find the derivative, put the value as minus 2 iota for z, and this is the result I get. So the evaluation becomes very simple. You have poles of higher orders, as you are saying, and you are checking the contributions towards the particular integral that you're evaluating. So you're automatically doing something, you're doing all these things, and then later on you're going to give them names. You're going to define them as, let us say, residues and so on. You're going to give all of them names, but you must understand how you started. Please remember, I'm repeating this again. You started with a function which was non-analytic. The function was non-analytic, it became path dependent. The moment your function was analytic, it became path independent. The moment you had something path independent, Cauchy's theorem, Cauchy's Gorsuch theorem comes into play. And Cauchy's Gorsuch theorem comes into play when you talk of simply connected regions. Then you go a step further. You talk of the function, you talk of the derivative, you get the Cauchy's theorem. Cauchy's theorem says your function is analytic, the derivative is continuous, and you can work whether in a simply connected region or a multiply connected region, the integral over that function dz is going to be 0. Then you go advanced, one step ahead. You apply the Cauchy's integral formula for a simple pole and a higher order pole. We will go to poles, what they are, we will do that again. But we come to the Cauchy's integral formula just by this special formula, which gives us the information that we can calculate all the higher order derivatives in that particular region in question. So this is really a marvelous thing which we do in complex. Okay. Now, we also have Cauchy's inequality, Alevali's theorem, and a fundamental theorem of algebra. I'm not going into the proofs of them, but we're just going to get an idea of this right now. So Cauchy's inequality, again, requires that the function is analytic. And the function has an upper bound m on C. And when it has an upper bound C, then it says that the nth derivative of the function is going to have an upper bound which is going to be less than equal to m n factorial r to the power of n. Remember this is the radius, this is a region where you're talking about this function being analytic. So you have the region, you know this information. This is an n factorial depending on the nth derivative. So the nth derivative has a link with the upper bound and the n number, the order of the derivative that you are getting. So this is a very important thing when you are going to look in for transformations. Then we'll come in for Alevali's theorem. Alevali's theorem states that if a function fz is entire means analytic, having a derivative everywhere, okay, well defined, and it is bounded for all values of z in the complex plane, then this function is a constant. Now, no entire function except a constant is bounded. And in our last lecture, we have checked for sin z. I plotted the contour graphs for you and shown you all this. Again, now we extend this further. You might understand strong implications in physics later on. You might like to, read about Schwartz crystal transformations and so on. And it is there these things are going to get applied. Okay, so when we talk of fundamental theorem of algebra, we know that that this n should not be equal to 0. And if I'm talking of any degree n greater than equal to 1, I have a part 2 attached to the polynomial, which says that it should have exactly n number of roots. So we know these qualities, okay, which we will use. But before that, because I want to discuss the poles, and I also want to go into the argument theorem. So let me first discuss what is a pole. Pole by definition is given like this in the books. Okay, so but what's the meaning of this? Excuse me. Okay, so you have a function here, let us say 1 upon z minus 3 whole to the power of 5. The moment I put z is equal to 3, this function blows up. So I say that z is equal to 3 is the point of singularity. But if I multiply by z minus 3 to the power of 5 with fz and calculate the limit at z equal to 3, which was the point of singularity, do I get a value? I do. In this particular case, I do. And that value is going to turn out to be 1 and it's not 0. So it means that I have at z equal to 3 a pole, but of which order? Of order 5. Because I have to multiply by z minus 3 to the power 5 with fz to find out a limiting value. Otherwise, I'm not going to get it. So conceptually, what we do is we can always write a function as some phi z upon z minus z naught to the power of m, keeping in mind that this phi z will neither have a pole nor a 0 at z naught. Why? If it has a 0, it's going to cancel off with the denominator. The power will reduce here. And if it has a pole, what am I studying about? Because if I'm studying about a pole, that pole should sit in the denominator. So I need a function which is completely analytic here, phi z, because I will multiply by this factor here with the fz, find out the limit z tending to z naught, and that limiting value I will apply on phi z, which should be an analytic function, should give me a result. So that is the idea of the pole. So very clearly, the pole is this order m that I'm getting, and it is this n which is written here, and it's always going to be a positive integer. If your n is 1, you call it as a simple pole. If your n is larger than 1, you call it a pole of that particular order. So that's the thing. Okay, so let's just use the argument theorem. This makes your job very easy and very fast. If you have a function, and this function is analytic inside and on, again, a simple closed curve C, except for a finite number of poles inside C, then integral, I mean 1 upon 2 pi iota times the integral over that contour, the derivative of the function is in the numerator. Please see that upon the function dz is equal to n minus p. Now what is n? N is the number of zeros of this function which is sitting in the denominator. And p is also the number of poles of this function which is sitting in the denominator. However, we can sometimes, if you see this example on top, this has a pole of order m at z naught. So that means it has a multiplicity of m. So I can also use the multiplicity in writing the number of poles. So actually what we have to do is we have to count the total number of poles and count the total number of zeros and put that in this particular expression. So the idea is how to use an argument theorem and how to apply it. So let's do an example on this. Okay, let's find an integral tan z dz. Now, if I write tan z, it is sin z upon cos z, and the contour that is being given to us is mod of z is 1.2 times pi. Now, if you look at the functions, this function sin z is an entire function. We know that. Cos z is also an entire function. We know that. And sin z and cos z, both of them do not have poles. They are just totally entire functions. But the idea is we want to use the argument theorem. And when we want to use the argument theorem, we must see the function that we have in the denominator. What do I see? I see the function as cos z. So do I have a derivative on top? I have, because the derivative of cos z is minus sin z. So I can just put a minus sign twice. I have the idea there. Okay, so I can apply the argument theorem because f dash z upon fz is n minus p, and that 2 pi iota I just cross multiplied. So now what do I check? My function in question is this cos z. So this cos z, I will try to see where are the zeros of this cos z, because they are going to give me the poles for tan z. So zeros of cos z are plus minus pi by 2, plus minus 3 pi by 2, plus minus 5 pi by 2. But how many of them lie inside this contour of question? So only minus pi by 2 and plus pi by 2 are going to lie inside. So only these two are going to contribute. So number of poles, 2, right? Number of zeros, zeros of cos z, I'm getting here plus minus pi by 2. There are basically no poles in cos z because they're entire functions. I'm repeatedly saying that. Okay, so P is basically 0 and n number of zeros are 2 in number, minus pi by 2 and plus pi by 2. So what you have to do, you have just to put the count 2 and this P is 0 and you have found your integral. It becomes a cakewalk if you know this kind of contour integration, and it is really very useful, really very useful. Okay, so now let's come over to a power series. Now, a power series is anything that you write in the powers. Let us say, if I want to use A as a reference point, these CMs will be the constant coefficients, and I can write Z minus A to the power of M. I can just open it up like this. But as we did in our last lecture, we must talk of this Z minus A converging in some limit. Let us say it is converging, let us say less than some R. What is this R? We don't know, but we'll just find out what it is. So Z is a variable. All these C0, C1, C2, and so on are constant coefficients. If I take the reference point as 0, I can write this series also. But how do we check for the convergence behavior? you can read it from the Weierstrass theorem also, and you can also understand from the D'Alembert's ratio test. And the ratio test is very simple. It says that if you have a series like this, just find out what is the Rn plus 1th term. This Rn plus 1 means the n plus 1th term expression divided by the nth term expression. Calculate the limiting value of the modulus of that. If it is less than 1, then the series is going to converge. If it is greater than 1, it diverges. When it is equal to 1, you cannot say anything about it because the series is indeterminate. Okay, so we usually use this concept. When you use this concept, look at what I wrote. I wrote z minus a mod should be less than some radius of convergence, which I'm calling it r, could be infinity also. Okay, so what was the idea? The idea was if I have z minus a to the power of n plus 1 upon z minus a to the power of n, I'll definitely have z minus a less than some value as 1 over here. So this radius of convergence you can choose as 1, you can choose as whatever you like. That is what it's going to tell you. Okay, as long as your n tends to infinity, if this ratio is less than 1, the series converges. So let us just try some examples on this. For example, we have a geometric series like this, summation z to the power m, 1 plus z square, and so on, right? So we have a series like this. Here we have a series. Now we want to check how it's going to converge. So z n plus 1, calculate that. That is the n plus 1th term, calculate the nth term, calculate the mod, calculate the limit. But limit when? When your n tends to infinity. That's what you do. So if you do that, you will find what? You'll just get a mod of z less than 1. And this tells you that your series is going to be absolutely convergent in this particular region. Okay, let's have another series. You have a power series z to the power m upon m factorial. You open it up like this. Okay, and you check for the n plus 1th term. You have here, you have the nth term, you have here, limit n tends to infinity, you have this expression. So this series again is absolutely convergent for every finite z, as long as obviously it's following this rule, which it is. Now look at this one, this power series. This m factorial was in the denominator. I just multiplied the m factorial here along with the function. So this is how it's opening up. But this tells me a different story altogether now. N plus 1 factorial z to the power n plus 1 upon n factorial z to the power n. Take the limit. What do you get here? Now this tells you something else. It converges only at z equal to 0. Because the moment I put n equal to infinity, this is going to turn out to be infinite. Right? So you have sometimes to check for the power series where it is converging, where it is diverging, at what particular region or domain is it going to give me a constructive answer, because it is very important in which domain you are working whenever you're solving anything. So for example, if we understand from this power series concept the concept of Taylor series, in the Taylor series, what we are going to get here is that if you see this region that I've drawn here, consider this region to be a simply connected region. That means the function is going to have a value everywhere on this simply connected region. It is not going to blow up. It is going to be analytic. So anywhere I can find out the value of the function as f of z by using a reference point a, right? So if the function fz has to be an analytic function, which it will be, in and on the simple closed curve. If that is the case, I can write the functional value in terms of a reference point, which I chose as A, and write this expression. And this series is always going to converge for some radius of convergence R, where R I will define now. Okay, so R is going to be the radius of convergence, and it's going to be the distance from the reference point to the nearest singularity of the function. Now, this is important. The first singularity which occurs from your reference point that region is your radius of convergence. And if you do not write this series has no meaning, because a series is always domain dependent. It is always dependent on the region in which you are writing. It depends on the radius of convergence. So the series is going to change, and you're going to see it today when we are going to solve for the Lorenz series. The moment I will change the domains, everything is going to change. Okay, so now another thing, if your z minus a is greater than r, the series is going to diverge, and if your nearest singularity is infinity, then the radius of convergence is infinity. You can also adopt by choosing a as let us say equal to 0 as the reference point, and then this Taylor series gets reduced to what you know as the Maclaurin series, and you can just find out the functional values here. Okay, now look at this. I mean, it's really interesting. I'm sure you have learned Taylor series when you write your real functions and so on also. But you must understand that there are real functions that have derivatives to all orders, but they cannot be represented by a power series. So a function as exponential minus 1 by x square when an x is not equal to 0 and f0 is 0, try to write it, you won't be able to write a power series for it. So there are many real functions like that, but in complex, you can do that, because the moment you have a simply connected region and you have a function and you know that you have a derivative of that function, you can find all higher order derivatives in that simply connected region. Okay, so that's the thing you are going to all the time exploit for a complex variable. Okay, so here's a short example for you. Find the Taylor series for e to the power z. So e to the power z, function, functional derivative, second derivative, all of them. I'm asking about z equal to 0 means find out e to the power 0. So you get all of them as 1. So all these values, fa, f dash a, f double dash a, all these values turn out to be 1. And since the reference point a is 0, I can just simply write it as this Maclaurin series, substitute the values, and I get the series. Okay, and I check the radius of convergence. My first singularity will occur at z equal to infinity, and hence mod of z is less than infinity. This is the region where this function is always going to converge. This power series is always going to converge. Okay. Now let us express the Taylor series for a function which is sine z, sine hyperbolic, cos, and cos hyperbolic. Now, it might seem to you that, okay, we have to solve 4 questions, but the trick is solve one of them, you get the other 3 automatically. So how do you do that? So let us say we have to calculate this about z equal to 0. So we are still calculating it about z equal to 0. So we can adopt the closest Maclaurin series for it. And we understand that mod of z should be less than infinity, which we will get here also. We will get it from here. So start with the first function. Your function is sine of z. Find out the functional value, comes out to be 0. Find out the first derivative. Find out the value at 0, 1, and so on. You get all the values. Right. So effectively, what are you getting? You are getting that the even derivative turns out to be 0. The odd derivative turns out to be minus 1 to the power of n. And hence you can, write a series like this. So when you can write a general term like this, because the oscillating one that you are getting with n, and you're getting z here as z cube, z5, and z to the power 7, that means you have a 2n plus 1 here. And in the denominator, you have a 2n plus 1 factorial. You can just simply write a series for sine z like this. Now remember, when you're writing a power series, a term by term differentiation and a term by term integration, both of them are allowed. So if you can do that, if I have found a sine z series, I just differentiate each term, I'll get a cos z. Now, if I don't know how to, find out the differential of sine hyperbolic z, and I just simply know this expression that sine iota z is iota sine hyperbolic z, the only thing I have to do is in the expression for sine z, I just replace iota z everywhere and use the property of the iota, which I know that iota square is -1, iota 4 is 1, and I will get this expression for iota sine hyperbolic z, and henceforth I will get this relation for, or the series for, sine hyperbolic z. Again, do a term by term differentiation and you end up with a Cauchy hyperbolic z. So sometimes you have to make your mathematical analysis so fast that you solve for one thing and you get information about the others also parallelly. Now here also I'm giving you some shortcuts where you can use the geometric series, and this is what we will apply a little later. For example, you want to write a geometric series for a function which is 1 upon 1 minus z and a function which is 1 upon 1 plus z. Find the nth derivative. That's the expression for the nth derivative. And calculate, let us say we want to calculate this about z equal to 0. Okay, so you're calculating this series about a particular point and your reference point is 0. So fn0 is n factorial because the moment I put this as 0, I get a 1 in the denominator. So this is the Maclaurin series we write. We substitute the values, and if you look at the convergence, mod of z should be less than 1. Now, what is the idea? For one geometric series, you get an expression. You know only this, and you want to utilize it for, let us say, 1 upon 1 plus z. So the only change you have to bring about in this expression is replace your z by a minus z, and you will immediately get this series. Now say I want to write a series for 1 upon 1 plus z square. So again, I know this 1 upon 1 minus z. I know the geometric series is summation z to the power n, and I know this is the region of convergence. So just simply replace my z by minus z square, and I will get this series, but the same region of convergence. Keep that in mind. So this kind of method that you have used, is a method of substitution. You replace z by minus z square, you get this relation. If you replace z by z square, you get this relation. So this corresponds to this, and this corresponds to this. You can also use the method of integration. For example, if you have a function as tan inverse z, now be ready for a question here because I'm going to ask you something corresponding to the last lecture. You have a function as tan inverse z, and the derivative of the function is f dash z is this. So you just now wrote here 1 upon 1 plus z square. So this is 1 plus z square. So this is the series you wrote here. So 1 upon 1 plus z square is this series, right? So you know the derivative and f dash z, and you have this series. So you can do a term by term integration. So your function is this integral of this. So tan inverse z is this value. Please note the arrow that I've made. You can write it in a summation form. You write this as a summation form, no problem. But this represents the principal value. How many of you understand that this represents the principal value? Because tan inverse z is giving a principal value has some indication. Why am I saying it is only the principal value that I'm writing in this particular series? Remember, you're working on complex frame. Okay, so maybe you can answer me later on because I do not know if there are any questions. I mean, this chat is not opening, so I really don't know if there are any questions or answers. So, okay, so keep this in mind. Tan inverse z, I said, is a principal value. This expression that you have got here. What in addition should I have written or put here for it to be a general result? So try to answer that to me here. This is a question I'm putting up, okay, for everybody. Okay, so okay, now let's go over here. By using the geometric series, also we can write a power series. Now you'll understand why I'm coming to all these things. Writing series is very important because you want to get a functional form in a very easy way, or sometimes you want to, from a series, understand the function. So those applications are very important in the physics when you're going to apply them, where we will see just now. Okay, So by using a geometric series, that means I can just write a function. If I have something like c minus bz, just write it in terms of, just take out something, this constant you have taken out, constant c minus a, and you're writing as 1 minus something here. Now this something is the assumed z that we can say, because this is 1 upon 1 minus z. Maybe I can call it a q. So 1 upon 1 minus q is summation q to the power n, and this happens to be my q. This is my q, right? So I just straight away put it here in the expression, and I can write a series for it. And this series is going to converge for this being mod of this being less than 1. Same idea you can apply by using the binomial series. You have a function as pz upon qz, it's a rational function. Just make partial fractions of this function, and each function that you have got here in the denominator, try to write it as in this form, 1 minus or 1 plus something. When you're able to write it in this form, after having taken out that constant and absorbed it in the a and the b, then what you can just simply do is this 1 upon 1 plus z to the power m, you can write in the form of a binomial series, and then you can use this series to represent or write a series for the function. This possibility is there. Now we come to a very interesting thing, which is your Lorenz theorem. See, so far what you did, uh, let me go to a blank PDF. You took a simply connected region, right? And you took a point Z. You took any reference point as A. This region was simply connected. Function was completely analytic. And you wrote a Taylor series for it. This is what you have done. Now the question is, this was simply connected, I had no problem. But now you are going to be in a contour, which is going to be multiply connected. There may be a singularity here. So in that case, you cannot write a Taylor. You cannot write a Taylor series. What you will have to do is you will have to write a Lorentz series for it. Okay. So how to write a Lorentz series? This is what we have to learn now. So we expand a function fz, right, in the form of a series. But about which point? About a singular point, right? So what do we need? Now look at this figure carefully. It's an annular region that is shaded here, which you see. And this annular region is between two positively oriented concentric circles, C1 and C2. C2 is the smaller one, C1 is the bigger one, okay? And we assume that there is a singularity inside C2. Fine. There may be a singularity outside C1 also. So all possibilities are there. We can have a singularity here, here, anywhere. So all possibilities are there. However, the point that I'm trying to make is, you have a contour C1 in the positive sense. You have a contour C2 in the positive sense. You have an annular domain, and you want to write a power series or a Lorentz series for this function. How do you do it? You write it like this. Now, very carefully try to look at this. If I did not have C2, if this was, let us say, not there, if I had only C1, then I would write a Taylor series. Then I would just write only this part. If you just see, I would just simply write only this part for this function if I only had C1. But the moment I say there is a singularity, and that singularity lies in C2, I introduce this factor, Bn upon z minus a to the power of n. This factor has been introduced. And this term or this series that you are seeing here is called the principal part of the Lorentz series. This part is the Taylor series expansion. Look at it. It starts from n equal to 0 to infinity. And look at this summation starts from n equal to 1 to infinity. That means you have z minus a cropping up in the denominator and all higher powers coming in the denominator. Look at this part. This is called the principal part. Now, the properties of these integrals. Now, look at this. First, let me remove all this. So, if I am saying that you don't have a singularity, you can write a Taylor series. So that means this an coefficient which is sitting here should have a dependence on this C1 contour. And this is what we see, that ANs are defined on the contour C1. This is nothing but your Cauchy's integral formula with your n 0, 1, 2, and so on. And Bns are defined on C2 where you have the singularity, but your n is defined from 1, 2, and 3 onwards. So this is the expression for Lorenz series that you have, this one. So you have a Taylor series part and you have the principal part. The principal part relates to the singularities that you study. Okay, so let us try to expand some function in a Lorenz series, and we have two regions. One is mod of z less than 3 and one is mod of z more than 3. So the shaded parts, we want to write the Lorenz series. And if I take the first part, there is no singularity here, and I'm just taking a region which is simply connected. So the function is 1 upon z minus 3. I just take a 3 common outside. Z by 3 minus 1 I'm writing here. Again, I can write, take out a minus sign here. This is 1 upon 1 minus q. Remember, yeah, it's written here. 1 upon 1 minus q, which can be written as a geometric series summation n 0 to infinity q to the power n. This is what I'm trying to tell again and again. We can use this again. So 1 upon 1 minus q, so expand it off. And this is the series expansion that you get in a simply connected region. Now, same thing if we want to do for a multiply connected region, or if I want to do for mod of z greater than 3, I have fz here 1 upon z minus 3. Take the z common. Now, you must understand why am I taking a 3 common out here and a z common out here? Because the idea is to keep this constant z by 3 that I have less than 1. Okay. If this is less than 1, that means I am in this region, mod of z less than 3. If I take a z outside, 3 by z is less than 3 by z has to be less than 1 for the series to converge. That means mod of z is greater than 3. So this tells me this region. That was the idea. The idea was to calculate in a simply connected region where mod of z was less than 3, and in the other shaded region here, which was mod of z greater than 3. So you have this series and you have this series. Now there is an important thing that you must note. If you note here, this series, this arrow that I draw here, this series has all higher powers of z. And this series has all powers of z in the denominator. If you multiply it, you have a z, z square, z cube, z4, and so on. So the moment I introduced a singularity at this particular point, it's cropping up here. But it's quite possible that it's not clear here because I drew here a dotted line. I also drew here a dotted line. And dotted line we have learned is that, for example, in this case, the contour where we are not going to include the points on this particular contour. So here also, I did not include the points on the contour. Here also, I did not include the points on the contour, but I'm writing the series valid for the respective regions. Okay, so maybe I go over to another example to make some things clear, because it's very important for you to understand that the moment I changed the domain, this domain was mod of z less than 3, and this is mod of z greater than 3. The form of the series representation for the same function has changed totally. Okay, so the behavior has also changed. So now this question is up here for you to analyze. You've been asked here to find all Lorenz series for this function 1 on 1 minus z square with center z equal to 1. Now, when I write with center z equal to 1, it means you have to have a series in powers of z minus 1. So you have the function 1 upon 1 minus z square. You can expand it. 1 minus z is already there. So what I need to do is I only need to concentrate on this part. and I need to expand this in powers of 1 minus z. I'll still use this concept of the geometric series, and I write 1 upon 1 plus z, but I do two things now. I can write 1 upon 1 plus z by taking out the 2 constant. I can also write 1 upon 1 plus z by taking out z minus 1. Okay, so let's do it. So this 1 plus z can be written as 2 plus z minus 1. You take out the 2 common, you have 1 minus and a minus of z minus 1 upon 2. I'm assuming this should be less than 1 because I want to use this property of the geometric series. And when I do this, it immediately tells me that I am going to use a domain where mod of z minus 1 is less than 2. So this series is basically going to converge in this domain. This is clear. This is for A. Similarly, 1 upon z plus 1, I again write it as z minus 1 plus 2, but I now take out the z minus 1. I have 2 upon z minus 1 mod less than 1 now. And now I can use the same expression for the geometric series and expand the series, I get this form. But this form tells me that it is applicable in this particular domain. So the disk in question is this, right? So you can write the series expansions for the function in both the domains. You have the function as this, right, in this domain. And you have the function, again, use the second B equation here, you'll get this expression. Now, let's just look at these two things. I mean, it's important for us to look at that. So I just want you to look at this equation, and I want you to look at this equation. Okay, so the idea here is the function here has a simple pole, z minus 1, all higher powers of z minus 1 here. It terminates at z minus 1, and this one starts from z minus 1 square in the denominator, and the powers keep on increasing. So at the boundary, you're not saying anything but less than 2, greater than 2. Okay, so maybe this just made an overlap. So this is less than 2 region, and this is the higher region that you have. So two different regions and two different annuli, same centers, but different Lorenz series. Exactly what we are getting here. Okay, so now let's classify the singularities. We have isolated ones in such a manner that if you have a region, and if you have a singularity, let us say you have a singularity at A, then you try to make a boundary about it. You try to choose some radius, let us say some delta radius about it, such that no other singular point lies in this region. Okay, so if you have z equal to a point of singularity, and if you have no other point of singularity in a region which you can draw about it, then that singularity is going to be called an isolated singularity. Okay, so the definition is very clear. If you can find delta greater than 0 such that the circle encloses no other singular point, then that point is a isolated singularity. And if that is the case, for every isolated singularity, you can write a Lorenz series in this manner, where obviously z minus a is between two annular domains, R1 and R2 being the radii of that annular domains. And this Bn expression that we are having here is the principal part of the function. So far for isolated singularities. Now let's come to non-isolated singularities. Now this is an expression of log z. Okay, this is a function here of log z. Somebody has asked me a question which I have just missed out.
Yes, ma'am. There was one question that what is the physical meaning of singularity?
Sorry, physical meaning of?
Singularity.
Singularity, yes. And there was one more question. It just cropped up. I mean, something on the Taylor series. I mean, it was a very long question, just went off. Okay. So the meaning of a singularity.
Should
Yeah.
I read it now?
Yeah, if you can.
Yeah, sure, ma'am. Yeah, the question says, ma'am, please again explain to me the difference between Taylor convergence only and Lorentz series having both convergence and divergence. If do like this, what is the applications?
Oh, okay. So there is a confusion here. The confusion should be cleared. The idea is you're writing a power series. Whenever you're going to write a power series, you're going to write it for a region. Okay. And if your series has to converge, it has to converge in the region question that you're asking for. And the check for any series that you have is the D-Alembert ratio test, which I have told you. You take the n plus 1th term, you take the nth term, you find the limit n tending to infinity. If it is less than 1, it's going to converge. If it is greater than 1, it is going to diverge. If it is equal to 1, it's indeterminate. 1 point clear. Second point, if you have a Taylor series to write, you write a Taylor series always in that region where your function will always have a derivative. A function will always be analytic, it will always be entire, it will always be defined. So you write your Taylor series in that particular region. This is most important. Now, where do you write your Lorenz series? You write your Lorenz series where you can identify that, yes, I have a region and I have some finite number of singularities. Note this word, this is very important what I'm saying, because I said that the singularities have to be isolated. So if you have a region, if you have a singularity, draw a small radius about it and circle it and isolate it. If you can isolate the singularity in such a manner that no other singularity sits in that particular region, then you can write a Lorentz series for it. So it is very important to have an isolated singularity when you're writing a Lorentz series. Now, when we talk of convergence, same story applies to any series that you write. So there should be no confusion about that. Now, the idea about what is a singularity. A singularity means I have a function, let us say 1 upon z. If I put z equal to 0, the functional value becomes what? Infinity. So infinity is an indeterminate or not defined thing for us. Though we did stereographic projection last time and we defined those points, but the idea is that the function is indeterminate. It is not defined at the point z equal to 0. That is the meaning of a singularity. Similarly, like I go ahead here, if I had taken log of z at z equal to 0, where is the singularity? If I say log z at z equal to 0, log of 0 is going to be where? Okay, maybe I can answer that. That is minus infinity. 1 upon infinity is going to be 0. So you have to understand that the point of singularity is 0. The value of the function is becoming infinite or minus infinite. Okay, so your function is not bounded. It doesn't have a boundary. It doesn't have a limiting value. It's just blowing up. So that is the meaning of a singularity. Very simple. And singularities have physical significances in a lot of things that you read. I mean, there's a lot of news about black holes and wormholes and, passing through space and passing through times and so on. So they're all different types of singularities that we talk about. So let us first talk of a non-isolated singularity. Isolated, you have learned, you just draw a radius about it and that becomes isolated. But what about a non-isolated singularity? So there's a contour graph here for you, and this is a three-dimensional figure. So if you recall the way we wrote log z, you must understand this graph. Can anybody try to interpret this? Because this is what I did in my last lecture for sin z. So if you can do it well enough, if you cannot, I still do it. Okay, I still have an explanation here for everybody to read. I'm saying that log z is a function which has a non-isolated singularity. Why I'm saying this is because it's written here. We say that every neighborhood means a close vicinity. That means a point very close to z equal to 0, which is the origin here, will always contain a point on the negative real axis where log z will not be defined. Simple meaning. But maybe I would like somebody to extend over it. What is the idea here? And what is the idea being communicated in this contour plot is this, that let me just write it. We learned this in our last lecture, that if I am writing a log of z, and this is a capital, I'm writing a capital log of z, okay? And how do I write it? I write it as, I'm really not able to write it right now. I don't know why my hand's not working. Okay, so let me try it again. I write here a log of z, and this log of z is log of mod of z, and mod of z, remember, is your r or x square plus y square under root, plus I write it as iota times the argument of z. And if you remember, argument of z was what? The principal value plus 2n pi. And you have the iota here. So this is actually capital theta plus 2n pi. And this is nothing but log of r. Now try to understand this. If your log of r is there, and I'm not talking of this for the time being, if I'm just talking of log of r, right? When I say log of 0, and this r means a real number. So log of 0 means I'm talking of something as minus infinity. So look at this. When you are talking of, this is a real log of r plot. Okay. So when you're talking of r, x square plus y square, r under root equal to r as 0, this dark color that you see is the negative value, r tending to 0. And as you go out, you're going radially outwards, right? So x square plus y square, which was your r, is your real constant, and you are just simply plotting here log r and trying to understand that. Now, what is all this happening basically? So what is this white line that you see? This white line that you see is effectively a branch line. If you remember, we used to write in the argument of z something between a 0 and 2 pi. We included the 0, we did not include the 2 pi. Or we said, okay, I don't want that range. I can use a range from minus pi to pi and so on. So all those things we have learned earlier. Now the idea is that firstly, if I take r equal to 0, I can actually not draw a neighborhood about it. I cannot circle it. I cannot isolate that particular singularity. And henceforth, it is a non-isolated singularity. That's the first point I make. The second point I make here is that because log of r, this r is basically a constant. So this can be an r, this can be another 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 r, and so on. The r is changing. Okay, so as I'm moving radially outward, the color is also changing, because the moment I go inside here, as r tends to 0, I'm going to get the negative values. It's going to blow up immediately, right? And same thing you observe here in 3 dimensions. You're going to have these surfaces up here, and the moment you are going to go deep into this neighborhood of x equal to 0, you cannot, isolate your particular singularity. Just not possible. Non-isolated does not mean movable. I do not know why you're saying movable. Maybe you had to write removable. Removable is a different kind of singularity. We will come to that also. Don't worry about that. This is right now a non-isolated singularity because I'm trying to explain to you Lorenz series. I'm trying to explain to you that Lorenz series can be written for isolated singular points. For non-isolated singular points, can we write it? Can we not write it? What kind of singular points can we use to write Lorenz series is very essential to understand. Okay, so that is why the idea of log function coming up here. Okay, and the main idea that I'm trying to make here is that this is a branch line, and these circles that you see are the sheets that you had. And the argument of z, if you remember, was the capital theta plus 2 and pi. So you take one circle round, you reach another sheet, and you cross over through this white line to the next sheet. So it's just like a spiral, you know, you go like this, you go like this, you keep on going and going and going, and this is what is happening. It's a spiral going on and on. So when you are going on this also, you are going on and on like this as a spiral. You're going about it. So the point here is the branch point. X equal to 0 is the branch point, the point of singularity. The name given to the singularity is a branch point. You have a singularity in the log z function at z equal to 0 as well as z equal to infinity. And maybe I think we have the time. Maybe I can actually, okay, since some students are getting interested, maybe I can just give you an idea from here. See, if you write log of z and you write the principal value, the log of z is log of mod x naught. Okay. So now you allow your z to vary on a circle. You allow your z to vary on this particular circle. When you vary it from 0 to 2 pi, your value goes from log x naught to log x naught plus 2 pi iota. So you take the circle. Look at this. You take this circle. You look at this hand that's going. This is a circle you make. And this is the branch line that I'm drawing here. And you have a transition from here to here. So when you are on the principal branch, you're in the lowest sheet, which is the darkest color that you saw, then the next color that you saw, and the next higher color, the brighter colors, and so on. But you must understand one thing, that this log z, which was infinitely branched because of this 2 and pi sitting up in the argument part. And another most important thing is that one must see is that this branch cut that you are calling, this cut that I have going up to infinity here, in this case going up to infinity, but the one that is drawn here in this figure is going to minus infinity. Okay, so there's a difference in both the things that I'm telling you here. Here, when you choose your range minus pi to pi, you can actually use this as the branch cut. When you use a range from 0 to 2 pi, you use this as a branch cut. So depending on the choice of the range for the argument, remember the principal range that we choose, you can have a branch cut specific for that. So branch cut is arbitrary. And what is the branch cut? It is that line, imaginary line, thought line, arbitrary line, when we can move over from one sheet to another sheet. We can just transit from one sheet to another sheet and correspondingly draw a Riemann surface. When you draw these lines, these curvatures, these become your Riemann surfaces. But the actual look is this. This is your three-dimension look of the log z function, especially when your z is a real number. You're talking of real z here. Okay. And if you see about the imaginary part, look at this imaginary part, what is happening? The argument is changing by what? 2 pi iota factor. So it changes by 2 pi iota factor, the deep color comes in, this is a negative color. So this becomes slightly lesser, and then slightly lesser, and then slightly lesser, lesser and lesser, and so on. It keeps on going. It's just like the petals of the flower, you know, one petal, and on top you put another, and you keep going like this. So this is what is happening here. You're not able to isolate the singularity. Another really interesting thing is that when you talk of singularities, if you remember, we did the stereographic projection. The point n, North Pole, was the point at infinity. So z is equal to infinity is also a branch point for log z. So if I take this great circle, look at this one from n to s, if I take this great circle, and if I'll take a projection on the extended complex plane, this is going to be the line in question, which I will call as the branch line. Okay, if I take this great circle, then I'll talk of this line. So the idea that I'm trying to make is that the branch cuts that you have, which you see here as a white line over here, depends on the principal range chosen here. Plus, you are getting an idea of the singularity, which is telling you that the singularity cannot be isolated. You can't draw a neighborhood about it. You can't choose a delta, which is positive number, which is very small, and you can say, okay, there won't be any other singularity. Because if you see here, maybe I can just remove this. Okay, so the idea that I'm trying to make is this dark circle that you see, you cannot, say that you have a singularity here, here, here. You have singularities everywhere existing. So they are all non-isolated singularities. Now let's come to poles. When you have poles and you have a Lorenz series to write, you terminate your Lorenz series at some power of m, because the pole by definition is what? Limit z tending to a, z minus a to the power n, fz should give you a result, a numeric value. And if I multiply z minus a to the power m with this function, the a value that I get should correspond to this bm. Okay, so if I have a pole, and poles are definitely isolated singularities, I can write a Lorenz series. The only difference is the Lorenz series will now be a terminating series, because all higher powers beyond here, whatever part I have in the principal part, they will all go to 0. So another way of writing a Lorenz series for poles is you write n equal to minus m to infinity. So obviously it's going to end up over here, it's going to stop here. Okay, and if your m turns out to be 1, or if I have a simple pole, I'll have the first term b1 will be called a minus 1, b2 will be called a minus 2, and so on. So for m equal to 1, it's going to terminate at the simple pole, which is going to be here, if I have a simple pole case. Okay, so if I want to find out the type of singularity in this function, we have to understand these things, because if you want to really solve contour integration, we need to know the type of singularity, and then only we can go ahead with it. Look at this, it has a power 3 here. So z equal to 5 has a singularity, but it is a pole of order 3. Z equal to 0 is the point of singularity, but because it does not have any power, I mean, the power is 1 for the singularity, so it's going to be called a simple pole. And obviously, if you are drawing this, z equal to 0 is a point which you can isolate here. Z equal to 5 is also a point which you can isolate here. They are both isolated singularities. One is a simple pole and the other is a pole of order 3. Okay, now what are essential singularities? Now sometimes students have confusion here also. Now essential singularity is neither a pole. The pole you have learned just now will terminate the Lorenz series at some mth value. It is neither a branch point, the log function had a branch point, or a removable singularity. Okay, it's neither one of them. Then the singularity that you have is going to be an essential singularity. Now, essential singularity may or may not be isolated. Both cases are possible. And in that case, when you write a Lorenz series, you will have infinite number of terms in the principal part. That means the bn's that you are having will go up to infinity. You'll have infinite number of values coming up here. Okay, so let's just simply take an example and understand what I'm trying to put across. So you want to find the type of singularity in the functions. Let us say you have a function exponential 1 by z. Just write a series for it. Obviously, you can see the point of singularity is z equal to 0. And it is an isolated singularity. But you can't terminate this series. Because you cannot terminate this series, it is an essential singularity. This is what we learn. Okay, now we have a function as tan 1 by z. Now tan 1 by z will have poles at these values. That means at what values of z? At these values of z. Now look at this, the values of z. Very closely look at that. 2 by pi is close to 0. 2 by 3 pi, closer to 0. 2 by 5 pi, even closer to 0. And so on is going to progress. So basically, you cannot identify a neighborhood about the point z equal to 0. That means you cannot isolate the singularity. Now, in this case, the singularity that you're talking about is a non-isolated essential singularity, because you can write a Lorentz series for it. However, it's going to be a non-isolated essential singularity. And this kind of singularity is actually, these are all related to cluster points. And maybe I'll not go into that right now. So the idea I'm trying to make here is tan 1 by z has poles at locations these, which are written here. You can change the factor of n pi, and that's how it's coming up here. And they cluster in the neighborhood, and therefore you say that there's a cluster point, and no Lorentz series can be written at the cluster point. Please remember that. You couldn't write it for log z, you couldn't write it for a cluster point. So these are things that you are learning. Now somebody had a question and wrote for removable singularity. So here it is. For removable singularity, what you have to understand is you're given a function which is not analytic, let us say at a point z equal to a. However, you can make that function analytic by defining the limit of that function at that singularity. And if that limit exists, then you can just simply remove it. And then you can write a Lorentz series which will not have the principal part component. So how do you do that? For example, you have a function sine z upon z. So you expand sine z because you know sine z is an entire function. You expand sine z. You have 1 by z, just divide it. What you see here is a Lorentz series, right? Then you find the limit at z equal to 0 for this. What you get? You get a 1. So you've defined a value, you limited it. So limit is existing. So this kind of singularity is a removable singularity. Now again, singularities are infinity. In the last lecture we have discussed. So I can just skip that off right now. So what did we learn? And again, I'm coming back to this again and again because students always have confusion between Taylor's and Lorentz series. And we are repeating it again and again. Your function is analytic. In a simply connected region, you have this Cauchy's theorem to account for all the time, that integral of the function dz is equal to 0. But the moment your function fails to be analytic, what did you write? You wrote a Cauchy's integral formula for it when you found out the nth order derivative and so on. So the idea is that when your function fails to be analytic, you need to find the contribution of the singularity towards the integral. And you give a name to this contribution, and the name that you give to the contribution, you call it as the residue. So how do we evaluate a residue? Because it's very important to evaluate a residue. So the contribution of an isolated singularity towards the integral, we are going to call as the residue. And for a non-analytic function, this integral is not going to be 0. You will talk over Lorentz series, and we will talk over domain of the Lorentz series. Okay. And if to be clear, if I'm just talking of a simple pole, I have a minus 1. I think these points are clear now. A minus 1 because z minus a, I will multiply with the whole function, take a limit as z tending to a, it's going to give me a minus 1. So a minus 1 is actually the name of the residue. So 2 pi iota times a minus 1 integral over the contour fz dz is the relation we are concerned with. And this comes from your Cauchy's integral formula. If you see this, if your n is, let us say 0, what did you have? What did you have here? A0, this constant. If it is minus 1, I'll have a minus 1. I will not have this term when I have n equal to minus 1. So I can write this 2 pi iota here. So 2 pi iota a minus 1 integral over c fz dz. This is the relation we are interested in. So a minus 1 is the name we give to the residue of the function. So let us just try to evaluate here and see how to calculate the residue of a function, something like this, by using Lorentz series. Okay, I'm not using any particular definitions right now. We will use them also, the definitions of the residues for higher orders, but let's just simply try to understand via Lorentz series first. So you have to find the integral of this function around this circle C in the counterclockwise sense. What you have learned is this. Maybe I will put it like this for you. We are interested in this. Okay, so this is the important thing we are interested in. This. So you want to calculate the integral. So integral is this. Function is given to you is this. So you just have to calculate the residue of this and multiply by 2 pi iota to get the integral of that particular function. That's the idea. So where's the singularity? At z equal to 0, and it's an isolated singularity, right? So z equal to 0, isolated, you can draw a neighborhood about it. You can do that. And now, okay, going fast, is it? Okay. So sin z, this is sin z, write the expression. 1 upon z to the power 4 is here. So put it inside. Now look at the coefficient of 1 by z. That's all you have to look at. And this coefficient is the residue, a minus 1. If you have a Lorenz series, a minus 1 is what? The coefficient of 1 by z. And put it here with the 2 pi iota, you have solved your integral and you got your result. So you use the Lorenz series expansion. You use the a minus 1, which you call the residue for the simple pole, okay? And you are writing it here and getting the final expression for the integral, okay? Now, let us have this question also. Show that the integral of the function this around a contour mod of z, let us say less than equal to, this should be 2 here, okay, this region. And it's described in the counterclockwise sense. And it says, tell me whether the integral is 0 or not. And let us write a series for it. So you know that an exponential z series can be written as z to the power n upon n factorial, but I don't have a z here, I have a 1 by z square. So I'll just put 1 by z square here and I'll just write the same expansion here. Now look at this series. It just does not have a term as 1 by z anywhere in the series. So the residue here is 0. So when the residue here is 0, I put it here, the integral over this function is going to give us a 0. So it's a direct application of Lorenz series that you are doing. So what we have learned here is that the residue is just limit z tending to a, z minus a, fz. If this is your function, so a minus 1 is the coefficient of 1 upon z minus a, and that is what we are calling as a residue as long as you have a simple pole. That is the thing. Okay. There's another shortcut. For example, if you had a function in the form of a pz by qz, it's a rational, let us say, it's a fraction that we have, and pz and qz are analytic at the point in question, which is z equal to a, and pa is not 0, but qz has a simple 0. So if qz has a 0, obviously qz will be 0 at some point of, let us say a is the point of singularity for the function fz. So that automatically implies that qz will be 0 at z equal to a. But I can write a Taylor series expansion for qz because I am saying pz and qz are separately analytic. So you write this, but if you notice here, q of a is not written. Q of a is 0. So you put the expression for qz here, pz is already there, and find the limit z tending to a and multiply it with z minus a with this. Everything, this z minus a, all this gets cancelled off. And the moment you put the limit z tending to a, all these terms go to 0. You are left with this expression, and this is a very important expression. So if you don't want to use a Lorenz series, you have a function which is a rational function where you have pz, qz, polynomials, sine functions, cosine functions, entire functions. But you have qz having, one particular 0 somewhere. So at that 0, you just have to calculate p of a upon the differential of q at the point A, and that is going to be the residue. Very simple. So for example, we have this. Okay, so maybe I should leave this. Can anybody find the residue at the simple poles for this function? And just give me quickly. By this definition on top, you can use this definition, the shortcut. The pz is 2 minus 5z, the qz is z square minus z. So differential of qz will be 2z. And you have to find it at the point of singularity. And the point of singularity, you have to tell me. Okay, so no answer. So let's have it. Okay, so if my point of singularity from here, if you write z
There is
square
one
minus
answer
z,
on the chat
sorry,
box. On the chat
sorry,
box, there is an answer on the chat box.
and the answer is
So yeah, so Smriti Chavla says this is 2 at z is equal to 0 and minus 3 at z is equal to 1.
okay. So why do I have a -2? You have to check it. Or this should be a +2 because I should have a 2z over here, right? So that's good enough, good answer. Okay, now this is a definition of the residue of the function of higher order poles. So this definition is again, if you can see this definition clearly and apply it for, let us say, the simple pole, that means your m is equal to 1, it is going to reduce to this expression. So the residue a minus 1 for any mth order will be 1 upon m minus 1 factorial, m minus 1 of differential of, this thing in the bracket, z minus a to the power m fz, and then you find the limit you find in the end, and then you get the expression for the residue, and this reduces back to the case of a simple pole. So if I want to find the residue of a function like this, which has a simple pole at, let us say, z equal to 2, but has a pole of order 2 at z equal to -1, again, I can do what? I can just multiply with z minus 2 here. This is the function, put the value at z equal to 2, I will get this as a residue. And for a higher order, the only thing I need to identify is this is pole of order 2. So I'm going to put the m as 2 or the k as 2 in this expression. So you put it as 2, you have a 1 factorial, you have first differential, you have a 2 here, you solve this, you get this result, right? So these are the ways you calculate the residues of the functions. Now, the point is that so far, what did you do? You found a singular point, you isolated it, and you found the corresponding residues. Okay, so, and you use the Lorenz series for it. Now, the question is, what if you have a contour which encloses more than one singular point, more than one isolated singular point? So in that case, you extend this idea of the residues by a residue theorem. And if you remember, we had a similar picture like this earlier also, when we replaced it, when we replaced the Cauchy-Gorsuch theorem for a multiply connected regions and so on, and we could write that the contour integration over C could be written as a contour integration over independent sums of the different contours we had from C1 to Cn. So if each one of the singularities that we have here, Z1, Z2, and so on up to Zn, can be isolated, and we can, just draw a simple closed contour about each one of the isolated singularities, then each one of the singularities will have a residue associated to them. So we can just simply write, let us say A1 is the residue corresponding to the Z1 isolated singularity, A2 is for Z2 and so on. So integral C Fz dz will be 2 pi iota times sum of all the residues I have from the isolated singularities. So please remember one very important thing, and this is what students usually kind of miss out on, is that this theorem is valid only as long as we are talking of isolated singularities. So you isolate them and you write them like this and you use it. Okay. So this is going to facilitate a lot of contour integrations and so on. So let us use the residue theorem and try to evaluate this integral now. Okay, and maybe we'll verify it with the Lorenz and the partial fractions to understand, because these are also two very important options available to us. Sometimes it is difficult for students to write Lorenz series, and it's more comfortable to write in terms of partial fractions. So if you see this function here, the integrand, it has singularities at z equal to 0 and z equal to 1. And what's the contour? The contour is mod of z equal to 2. And 0 lies inside, 1 also lies inside. So both the singularities are lying inside this region. Okay, so let us have a Lorenz series approach first. Lorenz series approach, now the function is 1 upon z, z minus 1. And if I want to write about z equal to 0, that means I need to expand 1 upon z minus 1 if I want to write about z equal to 0. Now, this is also going to help explain a student who raised a question about the region for Lorenz series. So maybe that person can concentrate here now. I write 1 upon 1 minus z as this series. This is just a geometric representation, and mod of z is less than 1. That's the geometric expression I have. But I now want to observe in the domain mod of z less than between 0 and 1, that's the annular domain. I want to write between 0 and 1 means I actually kind of draw this region. Okay, so I'm talking because I've isolated this, so I'm effectively writing a Lorenz series for this region. Please understand that. So this is the function 5z minus z. Okay, so I'm just writing this z minus 1 as minus 1 upon 1 minus z and expanding the series, and this is the expression I get. So what is the a minus 1 or the coefficient of 1 upon z in the function? The coefficient is 2. So I get a minus 1 as 2. So what's the residue? Residue is 2, corresponding to what? This singularity which was sitting at 0. And the region that I've used it is this. Why did I use this region? Because I have to isolate the singularity. I cannot include the other singularity in this particular region. Okay, so somebody asked me about the region for the Lorenz series. This is the way you identify, and this is how you specify that you have to take it from 0 to 1. Okay, now let's go. I mean, we have done it in this region. What about the other part? So let's do for the other part. Now, for the other part again, for the domain between 1 and 2. Now look at this light shaded one. We are going to look for this one now. In the light shaded domain, you just write again 5, I mean just writing it as 1 upon 1 plus z minus 1, because I want to use the center point as 1, because that's the point of my singularity. That's the idea here. That's the reference point. Okay, and you write this function in this manner, and the coefficient of 1 upon z minus 1 turns out to be 3, and this is the residue that you have. So residue for z equal to 0, I think you got as 2, and the residue for z equal to 1, I mean singularity at z equal to 1, you got as 3. So you write a minus 1, 3 for that, and you sum up the two singularities, multiply with 2 pi iota, and this is the result you have got. Okay, so you calculated at 0, you calculate residue at z equal to 1. Now let's have a different approach. Let's write the partial fractions for these functions. So if you write the partial fractions, they come out to be this. And very clearly, you can separately integrate them over the regions that you want. For z equal to 0, if you integrate this one, now you can apply, if you want, you can apply your Cauchy's integral formula, whatever you want to apply, you can apply all of them here. So this is simply going to give you a 2, and this is going to give you a 3. Now, how am I going to get that? If I use a Cauchy's integral formula, what is this? Fz. Fz is a constant. I have to find out f of a. F of a here is that constant, which is 2. So this is f of a. This is again f of 1, because the function is 3, the function is 2. They're constants, they don't change. Simply put the values and get it. Okay, so sometimes difficult for Lorenz series to pick up. Doesn't matter. You have partial fractions over here. Both of them lead to the same result. Now, you use the residue theorem to evaluate an integral of this type. Now, maybe I can skip this because we can, okay, maybe give you a slight overview of this. This is z cubed, so you have a pole of order 3. So the definition for the residue you will use is this one. You will calculate the pole, and if your contour is mod of z equal to 2, now you have to be smart enough to understand this question. If your this contour is mod of z, it's mod of z, first one equal to 2. So you have a singularity at z equal to 0, only this one is here. The other singularity at z equal to minus 3 lies outside. So I'm not bothered about it because it won't give me a contribution. So the only contribution I get is from this, which is calculated via a minus 1. And I just simply put the residue value here and evaluate the integral. And when I write z plus 2 mod equal to 3, you have to see which singularity lies inside. Okay, so if I have z plus 2 mod equal to 3, then you will have this simple pole lying inside the contour. So you calculate the contribution of this, right? And you have, even if you have 0 inside this particular contour, do you have that? You have to check it. And you sum up and you get your result. Okay, so we all have understood how to calculate the residues. So we also understand that calculation of residues is going to facilitate evaluation of integrals, and it's a very straightforward way. But what is most important for you here is the detailed shape of the contour was not relevant. Okay, the only thing that was relevant was you should be able to isolate the singularity, and you should be able to draw a neighborhood about that singularity. That was the only idea that you wanted to use. And the residue theorem you can use for evaluation of real integrals, and it really comes to your help when you're solving different integrals. So here's an improper integral. And the interval of integration here is not finite, obviously, as you can see here. You have an integral minus infinity to infinity. And please note, I'm now applying, I mean, these are applications of the residues. So I'm applying it on a real axis, fx dx. And if you can see, I can break it up into two parts, this integral, and I can approach from minus infinity and I can approach from plus infinity. So I'm writing a minus a here and I'm writing a b here, okay? So coming from two different directions, and I'm just, breaking it up into two parts here. Now, if both these two limits exist, we couple the two independent passages and just simply write limit r tending to infinity and write an r here and a minus r here. Fine. So please, this is purposely written here. You have to note that you are doing everything on a real line right now. So x is restricted to lie on the real line. Whenever I'm writing x, it means it is on the real line, right? Okay, now what happens? Look at this definition 0.3 and look at the definition 0.1. For some functions, the limit on the right-hand side of this exists, but this does not. For the second one, it does not. So let's see what cases. For example, I'm giving you an example here. You have a function as x. Okay, you find the limit r tending to infinity from minus r to r on x dx. If you just solve this integral first, and you find the limit r tending to infinity, this gives you a result as 0. So what have you done? You have done the third equation here. Now you talk of the different sets. I mean, you're approaching in different directions. So you have a limit from minus a to 0 fx, and you have from 0 to b. This is infinite, this is minus infinite, and this is not defined, right? So what comes to your relief? The Cauchy's principal value comes to your relief here. So principal value has a definition. It has a definition. It says principal value of an integral or a function which is defined on a real line is limit r tending to infinity minus r to r fx dx. And this expression that you see on the right hand side is the expression which is called the Cauchy principal value of the integral. And this is very much handy for us. How it is handy, we will understand now when we will apply it. So let us have an evaluation here for a function. And this is a rational function. Pz and Qz we are right here, keeping in mind that we are working for a Z, we're in the Z plane, but you can also apply it to polynomials Px and Qx of whatever degree they are. And see, we have some conditions here to satisfy. Now, what conditions we need here for Fz to satisfy are that Fz should be analytic. In the upper half plane, this is the upper half plane that I'm drawing here. Okay, I can choose it to be upper half. I can also choose it to be lower half. So one half. So because one half, so therefore we are writing upper half. Just take it as an example. So Fz is analytic in the upper half plane, except for finite number of poles. That means you have some singularities sitting up here, which you can isolate. But no poles exist on the real axis. Please note this point. This is very important. You have no poles sitting here on the real axis, because if I have a pole sitting on a real axis, then I will have to isolate it. So I will have to deform my path either by excluding it or by including it. Okay, so these deformations I will have to take. So because I'll have to take these deformations, it is the principal value, the Cauchy's principal value, which has come to my relief here. So the idea is right now we don't have poles on the real axis. We have just poles inside this upper half plane that we are taking into account. And we have r going to infinity. That means this is going to infinity and this is also going to infinity. Okay, why is it why do you need a half plane? And you'll get an answer to it right now. I'm giving that answer. I'm coming to that. How do you say r is infinity from minus infinity to infinity, and how do you draw it? If I am coming from minus infinity, and if I come to infinity, if I want to close it, I close it like this. If I close it like this, can I, assume minus? I mean, why should I take a circle like this? What happens? What happens if I take a circle? Why have I taken an upper half? There is a reason for it. Okay, maybe towards the end I'll tell you. Maybe somebody can think of it and tell me. And first, let me just apply this improper integral, and I'll give you an answer just now. Your function is analytic. It is analytic in the upper half plane. It has finite number of poles, no poles on the real axis, but it has one very important behavior, that if you have a numerator and if you have a denominator, the numerator will vanish as 1 by z square. That means if I have a polynomial in the numerator and if I have a polynomial in the denominator, the polynomial in the denominator should be 2 degrees higher than the polynomial in the numerator, at least 2 units higher. So only then you can apply this. Okay. So the contour S of integration for these rational functions, we are taking this minus infinity to infinity. We are not taking this. Okay, somebody has asked a question. I hope somebody is able to answer it. It's a very interesting question. from minus infinity to infinity. Please note this, your R goes from minus infinity to infinity. Can you write it on a number line if you're using this contour? I want to use the concept of Cauchy's principal value. I want to write an integral minus infinity to infinity fx dx is the limit r tending to minus infinity on fx. Remember, this x is on the real axis. And I'm saying that this is equal to 2 pi I times sum of residues in the corresponding contour. And the contour I chose is the upper half plane. If I take this contour, I am nowhere on the real line. And therefore, I must take that contour which includes the real axis. Okay, so that is the answer. If you want to calculate for a real integral, you want to calculate for fx, you need to do it on the real line. You need to calculate for this x. You need to take either an upper half plane or a lower half plane to include this part. Otherwise, it's going to be very difficult for you to do it on this. It's rather, I mean, you can't do it over here. Okay. So if you have to evaluate an integral from 0 to infinity, 1 upon 1 plus x4 dx, this is an integral you want to do. This is an even function. All of us know that f of minus x is fx. So I can just simply extend the range 0 to infinity as minus infinity to infinity and just write half of this integral. And now I extend this by an understanding that I can write this function as f of z. Right? If I can write this function as f of z, I can find out the poles because z to the power 4 will be minus 1. And I know how to write the poles. We have learned this thing. So if I'm able to identify the poles, I'll have a pole Z1, Z2, Z3, and Z4. Note this point now. You have 4 simple poles, 1, 2, 3, 4. But what you have to understand now is if you are working in the upper half plane, then you are working on this contour. Okay, the real axis and this S. If you are working in the lower one, you're working on this real axis and the lower one. That is how you are closing the surface. You have to close your contour. So if I have to take the upper half plane, the only two poles that I can include in this contour are Z1 and Z2. And I need to only evaluate the residues for these two poles, sum them up and multiply by 2 pi iota to get an integral minus infinity to infinity on the real axis, right? It's everything to be evaluated on the real axis. And to my savior can come this definition, the residue, just the function, the derivative of the function, the denominator, put the value of Z1, put the value of Z2. Okay, so you calculate the residue at Z1, calculate the residue at Z2. You have some respective values, put them up here, and this is your final result from minus infinity to infinity. But 0 to infinity will be half of this, and you have evaluated it. Okay, so I presume the answer is clear to the person who has asked me, why did I take a upper half plane? Because I'm trying to apply the residue theorem to integrals on a real line, minus infinity to infinity, improper integrals. I'm trying to solve them. Okay, now let us see here. If I want to evaluate an integral from 0 to infinity, 1 upon 1 plus x square whole to the power square dx. So you have this function, your function is even, right? So integral 0 to infinity, again, can be written as half of this. 1 plus x square means x square goes to minus 1. I need to identify the points of singularity. The points of singularity, if I write x, now why did I write a z? That should have been a question a student should have asked me. Because I want to integrate on x, but I'm writing a z. The moment I write a z, what did I do? I added a dimension. And I added this plane, and this contour and this shaded region I've added here. So that is the property that I'm using. And I'm using the property of the z and applying it to the x because A real number is a subset of a complex number. So I'm using those properties which we have done in our last lectures. So z square is -1. You have z as plus minus iota. So one iota here and maybe another one somewhere here. So this lies outside. I'm not concerned. I'm more concerned with the one which lies inside. And it is a higher power. So I will need to use the standard formula to calculate the residue. You use the standard formula and you get the residue value as 1 upon 4 pi. 4 iota, and finally you get it as pi by 2, make a half of it, and this is the expression you get for the integral. Okay, now let's evaluate some integrals. Let us say 0 to 2 pi, some functions of sine theta and cos theta d theta. We want to evaluate this, and we want to evaluate it for functions which we know if they have sines or cosines. Those functions will always be single valued. So the only important thing that you have to understand is when you're talking of sine and cosine functions, you're talking of a range from 0 to 2 pi. So you will be always considering contours as a unit circle. So when you were on the real line, you took an upper half plane or a lower half plane. When you have trigonometric functions to account for, you know that the periodicity is going to occur between 0 to 2 pi. So therefore, you will always assume your contour to be a unit circle. So every type of integral brings along with it the choice of the contour that you take. Okay, so now here you can define z as e iota theta, correspondingly sine theta, cos theta, and so on can be defined. You can change your functions into the forms of the z's here, okay, and those corresponding chains can be done. This minus iota, if you're getting, you can remove it outside. The idea is to use this and apply the residue theorem on all the singularities which lie inside that unit circle. Okay, so the idea is to use the singularities and the contribution of the residues towards the unit circle. Okay, so let's evaluate a definite integral 0 to 2 pi d theta 1 upon 1 plus epsilon cos theta. Now, this is an interesting question because this question has, so much of application that and a lot of shortcuts to long integrals. I mean, you'll see just now, we'll do it. So let us take z as e iota theta. dz, you know what it is. You can put the cos theta as z plus z inverse by 2. Make all your substitutions into it, and because your epsilon is less than 1, I'm keeping that in mind all the time. Okay, so you have this integral to account for. Leave this minus 2 iota outside. Look at the denominator of this integral, this integrand, which is epsilon z square plus 2z plus epsilon. And depending on the value of the epsilon, you can decide that the root z1 will lie inside the unit circle and z2 will not lie inside the unit circle. So negative sign, negative, negative makes it outside the unit circle. This plus sign brings it inside the unit circle. So that's why this lies inside and that lies outside. Okay, so this one is going to give a contribution towards the residue. So you calculate the residue at z equal to z1. It's a simple pole. So just simply apply this rule here and you get an expression like this. Very sorry for this. Okay, so you get an expression like this here. So the integral turns out to be 2 pi upon under root 1 minus epsilon square. Now comes the applications on long integrals. How do you cut your, something that you have learned, and how do you apply it on different integrals without actually solving the integrals? You have just now solved what? 0 to 2 pi, 1 upon 1 plus epsilon cos theta, but the condition was epsilon is less than 1, mod of epsilon. You can choose a fraction mod b by a less than 1. If you choose that and put it here, you get this expression. But the idea is you wanted to solve this integral, right? If you compare this integral and if you compare this integral here, the only idea was take the a outside, write a b by a, and check if your b by a is less than 1. If your b by a turns out to be less than 1, directly apply this b by a in place of epsilon and get this expression. Okay, so you have done this, right? So we assume you have done this. Okay, now you know this, which is a standard integral now for you. So you use this ahead now. Now your next quality is you want to evaluate an integral which has a square in the denominator. Earlier it was just 1 plus epsilon cos theta. It now has a square, right? And that epsilon, if you see, has been just replaced by an a, nothing special I did. And a mod of a is less than 1. But you just now solved an integral from 0 to 2 pi d theta a plus b cos theta, and this is 2 pi upon under root a square minus b square. The trick is differentiate this integral, right? This equality that you have with respect to a, both the sides. If you do it on the, why you're doing it? Because term by term integration that you have here, term by term, you can differentiate it also, whatever you have inside the integrand. This possibility is there, you know these properties. So utilizing those properties, you differentiate this with respect to a, you differentiate this also with respect to a, and this gives you this relation. Now you compare this with this, right? So what you have to do, you have to just put your a as 1, you have to put your b as a, and you have solved your question. Very simple. You used an integral you have evaluated, differentiated with respect to a, both the sides, you got this relation, but you wanted to solve 1 plus a cos theta whole square. So the only idea was whatever expressions you have, in that case, this a is 1 and this a is b. Put those values, you have your integral. Now again, this can be applied. Instead of a 1 plus a cos theta, I could have had a plus cos theta. So if I had a plus cos theta, I would still do the same thing. I know this integral. This is standard. I again differentiate with respect to a. And now, after doing that, I just compare. This a remains a, but the b becomes 1. That's the only change, and I have solved this integral. So sometimes we need to be analytically very smart to solve some integrals like this. Okay. So here we have an evaluation of integrals which are mostly useful when you're solving Fourier integrals, when you're going to be doing Fourier transforms, integrals, Fourier series, and so on. I mean, many things you're going to solve. And these are the applications that we have. So effectively what we are trying to do is we're trying to understand that an integral with a function fx, now this function can be a rational function, cos mx or sin x, any integral of this type can be replaced by exponential iota mx. See, you have mx here, you have mx here, right? So integral is from minus infinity to infinity on fx. Again, because it's on a real axis, I'll either take a upper half plane or I'll take a lower half plane. And I'm writing this as an integral from minus infinity to infinity. Only thing is this function has now been replaced by a rational function multiplied by an exponential iota mx dx. And m is any number, real and positive. Now you have two conditions, and they are diluter conditions than the earlier one when you had for the rational functions. It just says that your function should be analytic in the upper half plane. And it says that in the limit z tending to infinity, the function value should go to 0. And why this argument? Because you're taking the upper half plane. If you had taken a lower half, you would have written from pi to 2 pi. That's the only difference. Okay. Now, exponential iota mz is an entire function. We know that. So if you look at this figure, and if you try to correlate what is happening here, you are going on this path from minus r to r. This is what you are doing. You have fx, you have eimx, right, on this line. But when you are going on the s, which is the contour, you have fz and you have e iota mz. So this is corresponding to what is happening on the contour. because obviously your z is changing along this contour, it's changing here. But what are you saying? You are saying that this is equal to 2 pi I times sum of residues within the contour. And very easily, you can show that as your r tends to infinity, this integral that you have here by Jordan's lemma actually goes to 0. And when this goes to 0, the only thing you have to do is evaluate this integral, and it is 2 pi I times sum of residues of whatever singularities you had in the upper half plane. So once you do that by Jordan's lemma, you end up at this. Now, the question is, how do you apply the Jordan's lemma, and what is the idea? The idea is to make this term in the limit r tending to infinity go to 0. Okay, so how do you prove it? You prove it by symmetry. So limit r tends to infinity, I want to prove it to be 0. So I assume here a function which is less than equal to m upon r to the power k. Now this k is greater than 0, right? So if it is greater than 0 means I have the numerator and the denominator varying by a degree of r, r square, r cube, or anything, right? So on the contour, you will have z as r e iota theta because you've taken a contour from minus infinity to infinity. So it definitely has an r. You put the value of this z here in this integral which you want to evaluate, integral over s fz e I mz, and calculate the mod value of this r. This is the mod value you want to calculate. This is what you do. But using the fact that z is equal to r e iota theta, you are putting z here, you're finding the differential of this, and you're correspondingly getting these expressions, right? So you reach here, there is no problem reaching up till here. Now comes the understanding of, this less than equal to sign that comes up. Now what happens is, this when I take a modulus value of exponential iota something, that's going to give me a 1. What am I going to be left over with will be exponential minus mr sine theta. So it is this term which is important, which I have to figure out now. So if I plot a sine theta, I know this is the curve. And if I plot a y as 2 theta by pi, this is the line that I'm going to get. And sine theta will always have a value larger than, at any point that I take, the sine theta has a higher value than whatever value corresponding I take along this particular line. And sine theta sits in the numerator. So if I replace it by 2 theta by pi, this factor here, so this quantity will become what? Larger or smaller? Any answer? I know it must be a heavy lecture, but okay. So if sine theta is greater than equal to 2 theta by pi, and I make a substitution here, and this exponential has a negative power of something, so 1 upon e to the power sine theta, replace your sine theta by something which is smaller, makes this value what? Larger or smaller? Do we have an answer from anybody? Okay, so maybe we'll wait for an answer. I mean, I'm doing that, and by replacing this sine theta by 2 theta by pi, yeah, that's it. That's the answer. So I can always put less than equal to sign here.
So the
That
student says
possibility is there.
larger. Some of the students are saying larger, ma'am.
Yeah, I read it. Yes. So I'm using here a property of sine theta, the symmetry property, because about this pi by 2 sine theta is symmetrical. So this integral from 0 to pi can be replaced by an integral from 0 to pi by 2, and just bring a 2 outside here, right? So the idea I'm trying to put across is that you can solve this integral, and when you solve this integral, as r tends to infinity, this integral tends to 0. So effectively, you can evaluate any integral fx e I mx dx and write it as 2 pi I times sum of residues of the function in the contour of your choice. So for example, this is the probably the last question I'm putting up. And I would like students to just carefully look at this. It is very simple to understand it. You want to evaluate this integral from minus infinity to infinity, sine x square plus 1. I want to use the concept of this over here. Fx is 1 upon x square plus 1. Sine x I can write as e iota x and use this property over here, just corresponding to this, right? I can use that. And if I use that, I know my singularities are corresponding to x square equal to minus 1, which means plus minus iota. So it's only one singularity which lies inside the contour. So I need to take out the residue for that respective singularity. So if I calculate that, it comes out to be something like this, okay? And very clearly, 2 pi iota times this residue that I have evaluated, I get it as pi by e. Remember, subject to the condition that your integral over this s should vanish. If I can do that, I know this integral is equal to this. And the moment I know this integral is equal to this, exponential iota x means cos x plus iota sin x. Equate the real with the real, imaginary with the imaginary. You have actually solved two integrals in one go. But the most important thing is to understand how to show that the limit r tending to infinity IR is equal to 0. Right. So I have already proved it in the Jordan's lemma. The same application is done here. You put z as re iota theta, make all the corresponding changes. Calculate this, use your symmetry property here for sine theta, put these values up here, right? This and this has to do with the inequality, r square minus 1 and r square e iota 2 theta plus 1. If you see, this is z1 plus z2 modulus, and this is z1 minus z2. And look at this, this sign is changing. So anybody would like to answer this? I have an open question for everybody. Very simple to answer this. Okay, so this becomes this here, the denominator. Just carefully look at this. There's a modulus value here attached. There is no modulus value here attached. Okay, inequality is coming from here, so don't worry about it. I'm just talking about this denominator, how this comes here. Think about it. And once you solve all this, again, this tends to 0, and you are able to equate with the real and the imaginary parts. So it's just dot 8 o'clock. So if rightly, I haven't finished on time, but I mean, I am not going to summarize on any of these things because it's going to be a long summary. The books I have told last time also, and they're still the same. So if you would like to interact and ask questions, please go ahead, and I should write a proper thank you. Thanks for listening to me. I hope it looks like a thanks. Thank you. So open to questions.
This is such a lovely talk, ma'am. So there is one question on the chat box.
Yeah.
Okay, the books part the students wanted to see. Yes, so the slide is here. The students can see the books.
Yeah, the books are here. I've showed here, and you have problems in complex by Shams, that's Spiegel. Brown and Churchill, I've told them last time also, explains very well about the principal branch where students have a problem. And Krasik is again a book where you read a lot about branch points, branch cuts, and again you also have advanced calculus. Shom series, everybody knows, is a good book for solving problems. But as a physicist, if you want to read books where you can have a physical counterpart to whatever you have done. For example, I could not speak of that part right now today. but you have Afkin taking care of that. You have Skolnikov taking care of that, and you have Focus taking care of that. Okay, and then Greenberg has very good pictures which students can see and understand. Bowes is very simple to read and understand. Will also have very good, indications. So these are the books, and anything else?
Thank you, ma'am. There's so many
Questions?
thank yous already on the field. This was such detailed and a complex topic. So, uh,
Sorry.
if ma'am is here, ma'am is here.
Dr. Savinder,
Yeah.
please pass on this slide of, and if there is any other material which you would like to pass on to the students, they are from all over India and not just from Delhi University.
Okay, so
So
maybe I can just tell them to just go to our website. If you just type ssPhysics.com, and this is for anybody who goes there, you can just go to the website. You go to the resources, you will get something or the other new coming up here. And if you are not able to click on these resources, you can go
what
to
are
our
you showing? Are
alternative
you showing
homepage.
something? Are you showing something?
Yeah, I am.
But
Yeah, I did.
no, but where? I can see only your work cited and suggested reading.
Oh, okay. This is Zoom. I did not share the screen. I'm so sorry. So there is a website. Since you asked me to tell the students, there is a website they can note down, ssPhysics.com. So in the resources section, if they go, they'll always find something new coming up. And there is an alternative page also right at the bottom. So we have two websites linked to each other, which you can look at and download whatever you need. Yeah.
ssPhysics.com, right?
Yeah.
Okay. Okay. And if there is anything that you would like to share with the students, because every speaker is sharing either their PPT or handouts or some material, and at least a book of references with the students so that they can use it while they prepare their
I have
subjects.
actually given all the books. All the books here are available online. They can
Okay.
download whichever book they like. And depending on their capabilities, like I showed them a Focus. Focus is a beautiful book, and I think it is also in the syllabus of Delhi University, but I do not know whether other places. So these are books, you will get all of them online. So you should try to download the PDFs and read them. Try your problems as much as possible from Spiegel. It's going to help you. The more mathematics you do, the more clarity you develop, why this theorem has come, how that theorem has come, and all these things you learn. And what else would you like me to share, Dr. Punita?
It's up to you. Some speakers share their PPT. Some speakers give handouts. It's just
I mean,
dependent upon the speaker.
if they want this, if they want this, I can email it to you, and
Yes.
you
Okay.
can give it to
And
them. This PDF.
did you read this last question? Arya Gauri asked, "Ma'am, can you explain the last question once again, at least in the next class?"
Yeah, I don't have a next class. This is my
That is
last
why I'm
lecture
reading out
today.
this question. That is why I'm reading. No. You can
Okay.
always have a no. Dr. Savinder, it's up to you.
Yeah.
If you would be eager to take another class, I'll schedule it for you. It's not a
So,
problem. We
yeah.
need
So
willing teachers. It's not a
is
problem.
my screen visible? I mean, I
Yes,
can just
yes,
tell the answer
yes.
here. The
Yeah,
question
yes,
I had
yes.
asked here was actually, if you just see this is 1 upon mod of Z1 plus mod of Z2. Okay, this I think I'll write it in a clean place probably, or maybe I think it's clear. Can you understand this? I'll just remove this thing from here. Okay. So this r square e iota 2 theta is z1, and this 1 is z2. if you can figure it out. So mod of 1 upon z1 plus z2, this is what it is. What I asked you is, when you take a mod of this, how does it become 1 upon r squared minus 1? That was the question. And the answer to it is use your triangular inequality. You'll get your answer. It's very simple. Yeah. Any more question?
I'm now becoming greedy, and my greediness in learning more requests you that in case you take online classes for your students, kindly record them. We will link them to our Nasi Rally chapter, and they will have many more detailed classes with you, and they'll be able to view it from wherever they are, whichever state they are in. So I request you to let me have
I
a
will
link
try
of
that. I will try that, but I am not that savvy, but I'll try to do it.
Well, you see, just as the students have to learn so much, we the teachers also have to learn so much, and we are continuously
Yeah,
learning how to teach online. So our request remains, and if in future up till October middle, if you would like to have another class, I'll be only too happy to schedule it. Thank you so much. It's
Thank
a
you so
pleasure,
much.
Dr. Savinder. And as I said
Stop sharing.
earlier, also I'm lucky. I have wonderful teachers teaching here in a nice manner. And it is really nice that with such meticulous explanation, you give a new dimension to mathematical physics. Thank you so much. So I, along with
Thank
my
you very much.
organizing team and the attendees, so the students are writing, we would really wish to have more classes. So you see, I'm not making unnecessary compliments. My
So,
compliments have a root.
no, it will be better if you ask them the topics also. So maybe I can
Okay, students,
fix it on this
if
topic.
you have certain special topics in mind, post me on onto the WhatsApp group,
Yeah.
and we will request Dr. Savinder to take more classes after say 2 weeks or so. Meanwhile, so they say they are very helpful, and tensor analysis. Okay, they want tensor analysis if you would like, and so on. Okay. So it's like Aladdin's Chirag or something like that. You wish and you try. I try to arrange it. That's my work. Thank you so much. It's a pleasure to thank you, Dr.
Thank you very
Savinder.
much.
I do hope we
Thanks a
see
lot.
you again
Thank
before
you
we
so
wind up
much.
the series. Okay.
Yeah.
So, Dr. Neetu,
Thanks a lot.
Yeah, thank
Dr.
you
Neetu,
so much, ma'am. Thank you, ma'am.
Yeah. Thank you. It's been a pleasure, and thanks for the opportunity.